Good morning, everyone, or good afternoon, or good night. I don't know where you guys are located, but hello to everyone, and welcome to our first data science summer school organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support that made this summer school happen. And I'm extremely happy to see you all here today on the Zoom and on the parallel stream session on YouTube. I would like to note a couple organizational and technical details. In the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself or turn your cameras on unless you have a question. If you're in the Zoom meeting and you have a question, we really ask you to put the question in the chat first so that the instructor and the teaching assistants could see the question and try to handle it in the chat. Or you can raise your hand, but then you would have to wait till we have a break when we can give you a speech and you can ask your question. In the parallel YouTube stream session, you can ask your question in the live chat and we will try to handle this question as well. I should also remind you all that this Zoom session is being recorded, and thank you very much in advance for following these rules. And we shall begin with our third workshop in the summer school series, Modern Survey Methods, MRP and MRSP. And let me introduce you Professor Dr. Lucas Leeman, and he's an assistant professor of comparative politics and empirical democracy research at the University of Zurich. His research focuses on representation and how citizens' preferences translate into policies. His methodological work is concerned with measurement and surveys with a special focus on small area estimation. And Lucas, the floor is yours and you can share your screen now. Thank you.
Lucas, you're still muted.
Perfect. Good morning, everybody. Thank you very much for joining in. Thank you, Philip, for reminding me to unmute myself. So today what we're going to do is talk about multi-level regression and post-ratification, also known as MRP. I'm going to start out with the motivations. There are different motivations for different people why they would want to use this. And then we're going to do a building block, go back and see something from statistical theory that we're going to need. And then we're going to go in and build up this model and see how it works. And then towards the end, we're going to discuss extensions of this like basic model and see how we sometimes can get more by maybe not turning to Mr. P, but rather to Mr. P's better half, which is Mrs. P. And we're also going to see the latest addition to that family P. Okay, so in terms of motivation, why you would even want to go and spend some time learning a new model and the new approach, there's two main motivations that come out why a lot of people in the last couple of years have turned towards MRP and are using this. The first motivation is mostly an academic motivation. And that is that we have a plethora of nationally representative surveys. There's a bunch of election surveys carried out in various countries or other survey projects. But very often we are maybe less interested in just a very accurate estimate for a national average. But what we really would like to have is the ability to break that public opinion down into the subnational components. On the one hand, that might be something you need because you're working on topics of representation and you want to see how that differs and how that then may also differ in terms of how opinion is translated into policy. But it might also just be a descriptive step because you want to be able to show how cleavages in a society across subnational units are configured. So the first motivation why one would want to use MRP is the ability to take a survey that was intended to be nationally representative and to be able to still use that data to come up with very good estimates of subnational public opinion. The second motivation is partly academic, but is also strongly fueled by industrial interests, and that is that we face in the traditional survey world a challenge. So long gone are the days of George Gallup and the simple surveys where essentially you would call or contact people via mail and you would have a very high response rate, and then you could pretend that this is as if random. So what you see here is a figure from the Pew Research Center with these response rates. And you see that when we go here to 2012, and this is like almost 10 years ago, we fall very low. Now here we're somewhere around 10%. Individual surveys might be a little bit higher or lower. But the challenge that comes with this extremely low participation is that the assumption of as if random is no longer tenable. So what we face is that we often have samples, but we know that they are strongly affected by self-selection into the sample. So just assuming that these are randomly selected people and then analyzing the data that way is not going to be a very good approach to try and learn something about the structure of public opinion from such data. So if we go to that first motivation on the subnational level, then you might hold for a moment and say, well, do I really need that? If data is truly randomly selected, then in expectation, of course, that estimate that I get for a subnational unit, that might still be good. How would I get that? Well, I would just do what is known as disaggregation. So you have your 1,000 people, and then let's say you have 50 subnational units if you're in the US. And then for the state of California, you're always going to have a lot of respondents because it's a very large state. And the average of a specific item for Californians is probably going to be, the sample average is probably going to be a good estimate for the mean of California. But you're also going to have smaller states, Montana or something like that, where you're only going to have a handful of observations. And that's going to get you into trouble. So on the one hand, you're going to have a very high uncertainty around that specific estimate because you have so few observations. And so this is an issue that has, of course, come up again and again in political science and in other disciplines. And one response or immediate step to take against that is to try and build something known as a megapole. So if you're interested, for example, in capital punishment, the death penalty, and how people think about the death penalty, then you might be able to find a lot of different surveys that ask the exact same question. And then you can start and merge all of that data together. And then suddenly you might be working with a sample that is much, much larger. And then even for these smaller subnational units, you're going to end up with a sufficient number of observations that you would feel comfortable for a specific application using that. That is, for example, the strategy that Erickson et al. In their State House Democracy book chose in 1993. Now, the obvious caveat here is you would have to find a lot of different surveys that ask exactly the same question. That's going to work if you care about capital punishment. That's not really going to work for more specialized questions that you might be working on. And then there's, of course, another strategy, and that would be to use something known as post-ratification or raking, where the idea is that you try and come up with estimates for specific types of people. So you could imagine you distinguish between men and women, and you distinguish between highly educated and not highly educated people. And so that will create 4 different types, like women that are highly educated, women that are not highly educated, men that are highly educated, and women that are not highly educated. And then you take your sample and you estimate for each of these groups the sample estimate, the mean, and then you go to each subnational unit And based on census information, you know the structure. So you know how many men, how many women live there, and you know also what their educational level is. And then you weigh each of these estimates by the share of that type. Now you can do that, and that's going to work well if you have a situation where the difference between two subnational units is really fully driven by socio-demographic differences. But if you think about political attitudes, and maybe even a step higher, something like political culture, then there seems to also be a non-individual aspect to it. There seems to be something that changes over space. And so even though somebody might be highly educated, that doesn't necessarily mean the same if they're living in a dense urban area or if they're living in the countryside. That might also not be the same if they live in an area that is economically thriving or if they live in an economically depressed area. And so if you were to use the second strategy, you would miss any opportunity to take into account that some regions, even controlling for sociodemographics, just appear to have slightly different structure of public opinion.
Lucas, we have one question on the mega polls or mega surveys, whether there are time limits. I mean, how far apart these surveys can be in time for you to still use them.
Okay, perfect. Yes, so that's exactly one of these then practical problems that comes up, apart from the fact that you need to have ideally the exact same question formulation, which is of course not always given. So even though you would think asking for attitudes and capital punishment, if you go into different surveys, you will see that there's slight differences in wording, and that can already affect the responses. And the second point is what you mentioned here. That's right. How far apart can these things be? And that's going to partly depend on your own assumption of how stable these attitudes are. If these are attitudes where we think they are very, very stable, then it doesn't matter too much if I'm mixing things over a 5-year span. But if you think about something like attitudes towards same-sex relations, then for a lot of countries in the last 15 years, you would have seen a dramatic change in attitudes, such that a lot of people that if we were looking at somebody similar 10, 15 years back in a survey, they would have been very critical and negative about it. And nowadays, they either say they don't care or they're supportive of same-sex marriage. And so in a situation where we have an item that is tapping into an attitude that seems to strongly change over time, we definitely wouldn't want to have a 5-year span there, because then essentially we're just like averaging over time and we're going to be missing things. Hope that is helpful on that question. So whenever you try to figure out how far apart surveys can be, you want to ask yourself, how stable do you think that attitude is that you're trying to capture? Okay, the second motivation that stems from the fact that we have a lot of non-representative samples. And also, even if we have high quality surveys in the sense of we spend a lot of money on inviting people and incentivizing them, we will still end up with low participation samples. And so here it's just really important to keep in mind that classic survey sampling theory rests on the assumption that the probability to participate is orthogonal to any outcome you're trying to measure. So if you want to measure, are people politically interested or not, and you call up people and say, hey, we're doing a survey on political questions, then there's a good chance that that assumption is not going to hold. People who are less interested will have a higher rate of rejecting your invitation, will not participate. And if you think about it, for a lot of things we care for, it is not so clear why the probability to participate should be independent of the outcomes we try to measure. Now, I will later show how this can be helpful if you have samples that exhibit some form of self-selection. But at the same time, I also want to warn from thinking that this is somehow the silver bullet and everything goes, and you essentially can just use any sample that you find. As long as you do MRP, everything is going to be fine. That is not the case. One way to think about that is that there's a lot of variation in what we mean by a non-random sample. So one example here, you could think about YouGov samples that are ran where we have much higher confidence. And part of that confidence stems from the fact that we see again and again these surveys in advance of some political event. And then you see the election results and you see pretty well how this matches up with reality. But then there's also like partisan polls, like the GOP was running polls on Trump, and how satisfied are you with that? And so when you look at these polls, they are, apart from the problems you have with question wording, they are distributed mostly among party followers. And so there you can do as much modeling as you want. It's going to be extremely difficult to ever model your way out of that issue. So MRP may help, but it will definitely not always help. And this goes to a deeper issue, which we're not going to be discussing in great detail today, but which is in general that once we left the space of the random samples with the high participation rates, we kind of lost a simple indicator or proxy for data quality. So 30, 40 years ago, looking at the response rate was a very good indicator if it was a random selection of people to have a hunch of how good a data set may be or not. But we don't have any of these ex-ante indicators anymore in this post-random selection world. And so right now, you're essentially left with ex-post indicators, meaning looking at companies or other surveys, looking at measurements you get out of these surveys in the past and comparing it to real-world events to see if this is somehow matching up or not. Okay. Taking a quick look at the questions here in the chat. Not entirely sure if I understand that question. So yes, there are, of course, people that will never participate in surveys, and that's going to add to our difficulties. And that's part of the story why we see that these participation rates are so low. The real problem you would have with survey research is if at any point an entire part of society would always refuse to participate. If that were the case, then you would also, with any model-based approach, fail to fully get at that. But we don't know of any relevant large enough group that consequently never participates in a survey. But what we do have is groups where we traditionally know that their proclivity to participating is much, much lower, whereas for others it is higher. Okay, so just to wrap up on the motivation side. First motivation, you have a national poll, but you don't primarily care about that national estimate. What you really want to have is the subnational estimates, because you want a much more focus on the variation across states or Bundesländer, cantons, or other subnational structures. And then you have the second motivation, that there's a general challenge for survey research, and that MRP is something that sometimes can help you to deal with surveys that exhibit some stronger forms of self-selection. But again, this is not a silver bullet such that it's magically always going to work. It can, but it will not always help. So what we're going to do today now are three different things. We're first going to take a look at partial pooling, specifically or technically random effect. So those of you who have maybe done some class on hierarchical modeling or multi-level models, you will be familiar with that. For those of you who have never done any multi-level modeling, we're just going to focus on a very specific element in multi-level models that is going to be helpful for us here, and that is a random effect. Once we have that building block, we can go into the second part, and that's where we're actually going to look at how this multi-level regression with post-ratification works, that MRP model. We're going to go through a simple stylized example, and then we're also going to ask ourselves quickly, how good is this MRP really, and see some comparisons with alternatives. And then the final part of the theory input here in the beginning is going to be that we're going to take a look at improvements to this baseline model. So there's improvements on level 1 and there's improvements on level 2. Level 1 and level 2 will become clear in a little bit what that is. Okay. Partial pooling, or what Gelman once called the secret ingredient to Mr. P. Think about this hypothetical example. So I'm here in Switzerland. We have 26 cantons. We have a bunch of surveys that we're running. And what I really would want to know is where people put themselves on a left-right scale. We can assume that this left-right scale is measured from 0 to 9, 0 being very left, 9 being very right. And I want to be able to come up with an estimate for each of these cantons specifically. That's the goal. The data I have is just one sample, and I have individual responses on that question. So we have overall N people in our survey, but for every specific canton J, we're just going to see NJ voters. And for larger cantons, that's going to be a larger subsample, but for smaller ones, it's going to be very, very small. So maybe we only have 2 or 3 individuals in a specific canton. The goal is to come up with an estimate for Y in a specific canton. So it's going to be the expected value of Yj. So that's the canton-specific left-right position. So the average left-right position in a canton. Okay, so if you now have to do this, come up with an estimate. There's 2 things that you could come up with straightforward, easily. And the first one is that you're going to say, I will just take the national average and use that for all the cantons. That's where, in a world where you're kind of assuming the differences you see in your data set, they're just like random noise, but ultimately there's no difference across cantons. Now, the problem with this, of course, is that from the get-go, we neglect any potential variation and think of that as noise. So that's going to be a really good estimate in the sense of efficiency. It's going to have very low uncertainty, but we're going to be building in bias here. The other alternative you have is to do what is known as disaggregation. And that is that you're only going to take the individuals that live in a specific canton J when you come up with the estimate for that specific canton. So you're just going to take the people from one canton, you're going to look at the average value you find, and that's going to be your estimate for that canton. So the good news is it will give you an estimate for every canton. The bad news is these estimates will have high variation because there's not that many people. And for some cantons, you're going to get huge variation to the extent where it's not clear if you can really then work with that. Now, ideally, we would want to have maybe something that is a little bit in between these 2 extremes. And as it turns out, there is a way to get there, and that is what is known as partial pooling. So let's look at this figure on the next slide, which shows some data here. So this is 1,000 people from the Swiss household panel in 1999. You see down here the 2-letter abbreviation for the 26 different cantons. And here you see from 0 up till 9 on the y-axis. That would then be our estimate for the left-right position of a canton. So the red dots with the long bars you see, those are the canton-specific estimates based on this aggregation. So when I want to come up with the left-right position of city of Basel, then I take my sample, I forget everybody who doesn't live in the city of Basel, and I'm left with a couple of people. I look at the average value, that's my estimate. And so you see that comes with considerable uncertainty because there's not going to be that many people. And then over here, I'm going to point you to this one and this one. These are 2 very small cantons. And what we have here in this specific sample is a situation where we just had a single individual, a single person. So that is why you see a dot, but you don't see any uncertainty because you can't come up with the variation in that canton to then compute the sampling variation. If you look at this at these red dots, then you see that you get a lot of uncertainty and it's not so clear how reliable these estimates are. On the other hand, the first solution, if you just take the sample average nationally and use it for every canton, that's what you see here. So this like blue line that goes all the way through with these dashed lines, that would just be the national estimate. And now you look again at this figure and you see, well, there's this thing between blue and red, the purple dots. And when you look at them, then you realize that these purple dots, they have less uncertainty than the red ones, but more than the blue one. And you also see that the purple estimate is between the red one and the blue one. Because what the purple dots are the realizations of a random effect. That is this compromise that we can get out of it. And as you see, it's not just like a simple compromise in the sense, oh, I'm going to take the national mean, I'm going to take the local mean, and then I add them up and divide by 2. That's not what is happening here. It's much niftier because you will see that for some here, the purple dot is very close to the red dot, meaning that estimate is strongly driven by the local information. But for others, look at this situation, the purple block is very, very close to the blue line, so strongly influenced by the national estimate. So what we see is in purple here, these random effects have the ability to sometimes go closer to the local estimate and sometimes closer to the national estimate. And it's not like random how they do it, it's in a very systematic way. It is whenever we have more reason to rely on the local estimate that the local estimate will get a larger weight. So I'm going to write this now down as if you were going to really estimate each of these things yourself, maybe with some data from the case or country that you care for or on which you work. So if I just wanted to get the national mean, then essentially I can just go and run a regression where I have a constant and the error term. And then the constant here is going to be the national average. And that's going to be our mean estimate for the entire country. The red dots we saw, these like specific local estimates, that is what you would get if you ran a model and you added dummies for all but one unit, plus you had a constant. And then for the one unit you didn't include, the estimate would be beta 0. And for every other unit, you would have to add beta 0 to the beta with the specific dummy for that unit. So you then end up with 26 different estimates. If you think about it, this is like the grand mean because it's just the overall mean. Then with the fixed effects, you get at this local estimate. And the compromise we saw before, that is what is known in multi-level modeling as a random effect. And this is how you think about a random effect. If you want to write it down, you could think of this as a model where you have a constant, and then you have an error term that only varies across J. So in our example, that's an error term that only varies across cantons. So for a specific canton, the realization of that error is always the same value. And then you have the error that also varies across individuals. Now, the difference from fixed effects, where we also have something that varies over cantons, is that this alpha j is not such that for every canton we fully estimate that value. No, what we do is we actually say this alpha j follows a normal distribution with mean 0 and has a specific variance. So it's kind of not as extreme as estimating the fixed effect for each local unit, but it's drawn a little bit towards 0. For those of you who have some experience with machine learning, you can think of this as a form of regularization.
Lucas,
Yep.
maybe if I can take you back a little bit to the sampling bit. So there's a question on representative samples. So some survey companies offer samples that are representative according to some variables like age and gender in the census. So is that something that would mitigate the problem of low response rates or not?
Yes, if you care for age and gender, then you're good to go. But we usually don't care for age and gender because that's what we get from the census office. When companies say it's representative for age and gender, what they mean is that they maybe use something like quota sampling. So they will on purpose construct samples to ensure that they have the right amount of young people, the right amount of women, the right amount of men. But so that is something that may be good. But if they construct the sample with that in mind, then there's no guarantee that that also applies to the survey items you might care for, as if, you might be studying trust in government during a crisis or something like that. There's nothing in this approach that will somehow lead automatically to the fact that that trust is then going to be not correlated with the probability of participation.
Yeah, makes sense. One more question, and that's on the partial pooling slide. If we have a color-friendly version of that slide. I think we don't, but maybe you can just go talk about what the main point was of that slide, or what you see on it.
This one, sorry, this slide here. Okay, so I'm going to go from most efficient to least efficient in terms of estimates, how the error is going to grow. So the most efficient estimate is going to be the national value we have here, or the grand mean as it's known, and that is this line with the dashes. And then for every canton, you see 2 dots. And for those of you, I should change that, that have a hard time distinguishing purple and red. The one to the left is always the purple one, and the one to the right is the red one. And as you will see, the one to the left for a specific canton is always between the one to the right and this national average. And that is because the one to the left, the purple one, that is the random effect realization for that specific canton. And the random effect has this very nice feature that it's kind of partially pooling. So it takes all the information from the sample, it takes the national mean into account. That's why we say pooling, But it's not that it just like mixes it together. It partially does so, and it depends on the specific data structure. And I'm going to get in a little bit to how that actually depends and why this has such nice properties. Yes, why is the variance term subscripted with alpha? That is on the next slide, a question in the chat here. Oops, sorry. That is because we indicate with this that this is a variance term that pertains to this alpha parameter here. Because it's not the variance that describes the variance over the errors, it's the variance of the realizations of these different alpha j's. That's why we subscript with alpha. And so, as mentioned, we can actually take a look how this compromise works out for us. So we saw random effect as something between this overall grand mean and these unit specific or local estimates you may come up with, for example, if you used fixed effects. As mentioned, if you have a few observations in a specific unit, then you would probably want to trust the overall mean a little bit more and use more of that general information, because if you only have one person in a canton, who knows, you might have just like tough luck, bad draw, got somebody who's super extreme and that is not at all informing you about that canton. On the other hand, you could also see that there's a lot of noise around your estimate. So you're very unsure what that local estimate really is. And if that's the case, then probably you want to like weigh the grand mean more. And so here, and we don't need to go in detail through it, it might look a little intimidating. I'm just going to walk once through this expression. This is not like a perfect equation or a definition of the model. This is an approximation to give you a sense of how these realizations of random effects work out. But the specific realization of the random effect for a canton is going to be built up of these elements. And if you for a second forget a lot of this gibberish you see, you look here, this is like the local mean, and this is the overall mean. And then you see that we have some expression here, some expression here, and then we're dividing by the sum of these two expressions. So what you see here is nothing else than a weighted average. It's taking two things, it's giving each of them a weight, and it's dividing by the sum of weights. That's just how we come up with a weighted average. So what we can now do is take a quick look at this weight and a quick look at this weight to see what will make the random effect estimate for a specific state, canton, or Bundesland closer to the local estimate or closer to the grand mean. So here what you see is that the more people you have in a subnational unit, the larger the weight for that local estimate will be. So the more people I have in a specific unit, the closer my random effect realization is going to be towards the local estimate. The larger the variance of y in a specific subnational unit, the less weight I'm going to put on that local estimate. And when we look at the second weight, then we see that the larger the differences of the local estimates is, the less we're going to be relying on that overall. So what you see here is the different elements that play into whether a random effect is closer to that national mean or closer to these different local estimates. And it's done so in a very nifty way for us, no? Because when we have little confidence in the data we have locally, we're going to put more weight on the other national data. We're going to use more of the information from other cantons to come up with our estimate in that one canton. And when we have more confidence in the data of that one canton, we're going to put less weight on all the other data. So that's how this partial pooling works.
And there's a question also on partial pooling in the chat.
Yeah.
It's whether there is a theoretical justification for using a data for a canton that doesn't come from the canton. So that comes from the national data.
Yes, so whenever we do partial pooling, that's exactly what we're going to do. We're going to pool data. We're going to take data that doesn't belong to that specific unit, and we're going to use it to come up with an estimate there. And we do so because there is valuable information in that other data that we have, and we want to be able to exploit that. And yes, there are, of course, some boundaries to that. There's an assumption of exchangeability, but that would probably take us another hour and is better placed in a class on hierarchical models. But you want to look for the term exchangeability if you go and Google or read up on this issue of using additional information. Okay, so this is essentially all like the stats theory you need, or the one relevant building block to look at MRP, multi-level regression with post-stratification. So historically, this was first mentioned in 1997. There's a paper by Gelman and Little, and what they were arguing is that we can do probably better. Back then, often the standard was to just do raking or post-stratification. But there's a couple of issues with that. So with post-stratification, there's a problem that can arise known as empty cells. So you might want to try to get an estimate for young, highly educated women living in urban areas, and you do not have any such person in your data set. If that's the case, then you don't have an estimate, and it's not so clear what you then do if you're just in this post-stratification world. So what Gelman and Little do is they say, well, wait, we can maybe, instead of just taking simple averages, we will have a model that we use to come up with these estimates for these ideal types. And then specifically with an eye towards coming up with estimates for subnational units or other small areas, they say we can then on top even add a random effect for that structure, which will allow us to tap into differences. And so this is what would like retain some of these local idiosyncrasies. So if we somehow believe even controlling on education, income, gender, a person in an urban area might be more liberal than somebody in a rural area, we need a way to tap into that. And one approach would be to have something like a random effect for locality or unit in which somebody lives. Now, MRP was surprisingly quiet around Mr. P. Didn't get used by a lot of people. The paper was there, got cited sometimes, but nothing much happened until like the second half of like the first decade, so 2000 to 2010, when a couple of people started working on it. And here mostly it's Jeff Lax and Justin Phillips and Chris Warshaw and Jonathan Rodden that had some papers. So Lax and Phillips have this paper on gay rights. So they wanted to understand attitudes towards same-sex marriage, but then also state-level legislation in the US. And you can imagine what you need is you need a good understanding, a good measurement of local preferences over same-sex marriage if you want to start looking at these questions. And that's why they were motivated to use MRP. And then what Warshaw and Rodden do is they actually show this doesn't only work necessarily for states in the US, but we can also, if we have a survey just in one state, use it to go down to electoral districts within that state. And so they do a bunch of additional illustrations to show how widely applicable MRP is. And then you get this nice quote from Peter Selb and Simon Munzert, where they refer to MRP as emerging as widely used gold standard for estimating constituency preferences from national surveys. And maybe 2-3 years later, it starts that you also see companies using MRP. And by now it has become pretty much one of these like standard tools we're using when we're working with survey data and when we're trying to come up with small area estimation. So when I say small area estimation, that's just generic for example, subnational units, but you might have a different structure that you care for. Maybe you're trying to get estimates for larger cities and not necessarily for like a unit, a larger unit, something like that.
Lucas, there's a question actually on this point, and it's whether partial pooling can be used to gather insights across nations or national units, across countries.
So if you're trying to get subnational estimates there?
I think the question is that the national unit sort of is the subnational unit, and then there must be some bigger unit. That's how I understand the question.
So there's definitely people who have done MRP on questions of EU support and tried to like exploit that you might have a survey and you have respondents from different countries and you try to come up with a country effect. One difficulty you might have is that when you're studying something like attitudes towards the European Union, that there's a lot of different discourses going on, and that is something that can be a problem for you, again, relating to this exchangeability. So where you need to have the belief that there is something in the structure of opinion that follows, let's say, age groups, that is somewhat constant over that space that you try to model. And that is something that might fail at that level, yeah? So it's not clear that maybe older people have different attitudes in a specific area, but it's very well possible that if we look, if we compare Northern and Southern Europe, that we find very different structures to that. Okay. So the two things that we get out of this MRP that seems to be really the support or explaining the support for it is, on the one hand, that's a much more efficient use of data. When I say efficient, then essentially I'm referring to good estimates that have low uncertainty. And if you think about this plot and you think about the purple estimates, the random effects, they're always on the left, then you saw that they always had less uncertainty than the one right next to them that was just based on that local information. So that's one thing that we, of course, always like, having more precise estimates. The other element is that we can also add level two predictors. And that's something that goes back to work by Warshaw and Rodden. They specifically looked at that. How much can we improve the quality of these estimates when we not only use the survey data and we know in which unit an individual is, but we add information about the units, what in the multi-level world is known as a level 2 variable. So a level 1 variable would be my age, my education level, my gender, and the level 2 variable would be something, for example, like the share of the government's revenue spent on education in the unit I live. And as it turns out, when we're trying to estimate preferences of people in units, it can be very, very helpful to actually know something about these units and allow the model to use that data to make our estimates better. So I'm going to go through a very simplified example. Imagine we first have our survey with N respondents, and then we're going to set up a very, very simple MRP model. Now, a couple of things here. First, we're going to look at a binary question. So it's something like, do you plan to vote yes on this question, or do you support the death penalty or not? Because we're looking at a binary question, the model we're going to use is going to be a pro-bit model. So this here is just a capital phi, is just indicating that we're putting this into the cumulative normal distribution. And hence here, we don't have y equals, we have the probability that y equals 1. So the probability that this person I answers yes, I support the death penalty, is then going to be modeled as the pro-bit of, and then we have a constant. And now you see that what we get back here is different. So in other models, you would have something like beta times x1 plus beta 2 times x2 and so on. But what we're going to do here is we're going to add a random effect for gender, meaning this is going to be a random effect that has two realizations. So y2, because most surveys just recognize binary gender categories. And so what we're going to do is we're going to give everybody that self-identifies as female, we're going to give one realization of this random effect, and everybody that self-identifies as man, we're going to give the other random effect. So what that allows us is to get at or to come up with estimates that can differ across men and women. And then we're going to have one for education. And to keep it simple, we're just going to think of low and high education. In reality, you would have many more categories. So this random effect is, again, just going to give you an estimate for low and an estimate for high. And we're going to add one for constituencies, subnational units. So what we have is we have two random effects on the individual level, and we have one random effect on the context level. Now, what I want to do is come up with an estimate for each ideal type. What is an ideal type? An ideal type in this simplified example is going to be a combination of these possible categories. So if I have men and women and I have high and low education, I'm going to get four different ideal types. High education women, low education women, high education men, low education men. And what I'm now going to do is I'm going to try to come up with an estimate of this pi JM. So JM here refers to gender and to education for a specific constituency. So for a specific area. How do I come up with that? Well, I use the realization of this gender random effect when I come up for the estimate for highly educated women. So I'm going to use the realization for women. Here I'm going to use the realization for high education. And then I'm going to add the realization of the random effect for that specific constituency. I add these things to our estimated model constant. And because we're estimating this as a pro-bit, I have to put it into a cumulative normal distribution. And what I'm going to get back is some value between 0 and 1. Let's say I get 0.61. What that would mean is that I assume that 61% of highly educated women in a specific constituency are supportive of the death penalty. Now, ultimately, the estimates for the ideal types are not the core interest. Our core interest is to come up with an estimate for a specific subnational unit C. How do I do that? I take these estimates of ideal types in that constituency, and I weigh each of these estimates by the number of people that belong to that ideal type in that specific constituency. So I need to know how many highly educated women live in constituency C. And then I multiply that estimate by the number of such people in that unit. Then I do the same for low education women, high education men, low education men. And then I divide by the total number of people in that unit. What this does is it will take into account whether in some units I might have more highly educated women, in others I might have less. And this allows me to then come up with an estimate of support for the death penalty in Unit C. So that is, in a very, very simplified manner, how we go about estimating an MRP model and coming up with constituency level estimates. Okay. Now, let's extend this a little bit. So let's think of gender, education. Let's add age. And now we're going to call this thing district instead of constituency. So this is getting a little bit closer to what we will actually be doing and then also doing in the lab. Now, let's walk through each of these lines individually to see what is going on here. So we're going to start at the bottom, age. Let's assume we have 4 different age categories, something like 18 to 34, 35 to 49, 50 to 64, and 65 to whatever. And that will partition society into 4 different chunks according to age. Then we're going to do education, and let's assume we have 6 different education levels, which is more realistic than just thinking of high and low. Then gender, we're still stuck in this binary world with 2. So we're going to get 1 estimate for women, 1 estimate for men. And now we're getting to this part that allows us to take into account level 2 information. I'm now going to say that the district is going to be, and now you see, I don't have 0 here, but I have something else. I have a random effect for region. So region could be something that is larger than state. In the US, you will often see that there's 4 different regions that they use. In Switzerland, we often work with 7 different regions. Each region is made up of several units. These are not necessarily administrative units. It's not such that like the government has a level on that region, but what it should be is regions that seem to be similar on many issues. And it makes probably sense to take into account that in the US, for example, the Deep South is just somewhat different than, let's say, the Northwest. So this is just going to be a random effect. So just something we're going to add there. And then you have this expression, beta times xn. And remember the districts, the subnational units we're trying to get at, for example, states or cantons or Bundesländer, they have the subscript n. And so what I'm doing here is, instead of saying that I just have 0 and then we have the realization of random effect, we're pushing this a little bit around. So what this means is we're allowing for the differences that go in here to not only stem from the random effect, but also from the region within such a unit is, and additional information that only varies across units. So here you could, for example, take the share of billionaires living in such a unit, or the amount of government revenue spent on education. Or in the US, it might be something like the share of African Americans, the share of Hispanic people, something like that. Okay. If we were doing that in Switzerland, then one thing you might want to add on level 2 is whether people are German speaking, or the share of German speakers you have in a specific unit. And why may that matter? Because from political sociology, we know that there's a lot of attitudinal differences from German speakers versus non-German speakers. And so that allows us to pick up on that structural differences when we're estimating attitudes. In the US, something you will see, a level 2 variable that is very, very often used, is the presidential vote share. That makes a lot of sense because if you think about the US, then most issues align on some kind of liberal conservative continuum. And so knowing that a specific state has very strong support for a Democratic or a Republican president is probably going to help you come up with a better estimate on specific attitudes. If you're tapping into an attitude that is not at all aligned with this liberal conservative continuum, then that variable is not going to do any good. Okay, I see there's a question in the chat. Okay, so first, we don't interpret the MRP model because we're really here in measurement. So we're not going to look at the individual elements and somehow assign to them any specific meaning like we usually do it when, in case of a well-identified research design, we might be able to directly assign a coefficient to causal interpretation. Here, we're in a completely different world. We're really just trying to do measurement. So the individual value as such of a parameter doesn't have any relevance to me apart from it allows me to eventually come up with these estimates for the constituency. So hope that's helpful on the question on interpretation. Now, thinking about partial pooling, and now that we've worked through how you come up with an estimate, let's think about what that means. So if I want to get the estimate of the average support of 20 to 35-year-old female university graduate in a specific unit, based on what you saw in the slide before, then that is going to be influenced by all people in that age bracket in my survey. It's going to be influenced by all women in my survey. It's going to be influenced by all university graduates in my survey. It's going to be influenced by all people from that unit. And it's going to be influenced by all people from the same region in which that unit lies. And the way it is influenced is because we've modeled this through random effects, and that was this partial pooling. So we're adding this additional information there. There's another technical question. Do these alphas now vary across individuals within the same cohort? Okay, yeah, so let me go back. This is important that this is very clear. Thank you very much for the question. So up here, let's take gender. J has 2 different categories. So there's going to be 2 realizations of this random effect. And they're fixed, meaning every single woman in my model gets exactly the same value on this parameter. And every man in my sample gets another value, regardless in which unit they live, if they're highly educated or not highly educated. So the alpha realizations are constant for that specific group. Education here has 6 categories, so we're going to get 6 numerically different realizations. For everybody in a specific educational group, that value stays the same. And it is only a different value if you have a different educational profile.
And there's another question also on the model. So whether it's a Bayesian model or it's a frequentivist model. And
yes, so the way we're also going to estimate that later is we're going to be using Glimmer, but you could also go Bayesian if you wanted to. There's a bunch of advantages. It's a little bit, there's going to be slightly more work to do it in a fully Bayesian setup. But if you're somebody who usually works with Bayesian models, then just go ahead and do that. So the way actually that Philip and Reto and I in our package work with the uncertainty relies essentially on kind of a pseudo Bayesian approach to come up with uncertainty then in estimates. But what we're doing here is set up in a frequentist way. Not sure what the question, what is the frequentist justification here, given the nonlinearity? Nonlinearity is not a problem for a frequentist model. No, you can go and add, you can go and estimate your binary models, frequentist or Bayesian. That is not related. The errors are not additive. Well, the errors are additive on the latent dimension, what would be like the Y star or something like that. Note, we are not up here adding them up and saying that's the estimate. We're adding them up on the latent and then translating it back to the observed level or scale by using the cumulative normal distribution. Okay, so this we've done. Yeah, the last part here, which is maybe important, is also to think through what this means in terms of ideal types. So when we're doing this, we're coming up with a bunch of different ideal types. So with 4 age categories, 2 gender categories, 6 educational categories, you're at 6 times 2, 12 times 4, you're at 48 ideal types. And then what you have is each of these 48 ideal types within each of the subnational units. So if you have 26 cantons, then you're looking at, what's 26 times 48? That's 1248, is that right? I think so. Philip, you correct me if I'm wrong, yeah?
Yeah, we have, I agree, but we have actually a question of this from the on this from the beginning. So
Yeah.
there was someone who noticed that the papers in the reading list have different, number of observations or number of rows for post-stratification. Essentially, the ideal type number multiplied by the subnational units, and was wondering where this comes from, for one. And as a second question, whether that impacts the speed of the estimation of MRP, but also of our package, as well as SRP.
Okay, so the question was different number of ideal types.
Yeah, so where the different basically where the different number of post-stratification rows comes from.
Well, I'm not sure which specific example the person is pointing to, but one explanation is that you might have groups of researchers that come up with different classifications for educational groups. So somebody might use a very fine-grained scale for education, where you have maybe 6 categories or even more, whereas somebody else does something very simple where you just get 1, 2, 3, like primary, secondary, or tertiary education. The reason why this sometimes happens is because people don't have access to better census level data. Remember, to actually carry this out, the survey data itself is not enough. What I also need is I need census data that tells me you will find this many women of this age bracket with a university degree living in this unit. And that might seem not so difficult, but you will quickly realize that it's challenging. So for example, in Switzerland, if you go to the Federal Statistical Office and you ask for income groups, because we have a good understanding that attitudes often are structured according to income. So income is also something we often have in surveys. So we would like to use that. Well, it actually turns out you can't get that combination of data with income. In other countries, you might have other examples for variables that are difficult to tap into. And then also, when you're doing it maybe on this highest level of subnational units, it's not too tricky. But if you go down to a specific state, that's work that Warshaw and Rodden, for example, have done, and then you look within these electoral districts, you will sometimes not get all this data for data privacy reasons. once we really go down to a very low level and you know age and education, gender, you might know income group and some other things, you have so much information that you can actually start identifying individuals. So in the Warschau-Rodden piece, when they're looking at same-sex marriage, they, for example, don't use age categories because on that low level where they're operating, the US Census Fact Finder doesn't allow them to retrieve that information on that level. And so that is one way that can explain why you see that there's a different number of ideal types, because within the individual dimensions of an individual, so education, for example, different groups come up with different numbers of categories. Okay.
And yeah, so the second question was whether this affects speed of the estimation.
Yeah, so that depends a little bit. If we're looking at something where instead of, let's say, 3 categories, you have 4 categories or 5 categories, that's not going to be like the big thing. That's not going to affect you tremendously compared to whatever the baseline time is you need to run one of these models. And even if that were so, you probably wouldn't want to start collapsing groups just to save 5 minutes on your estimation. Like you want to make that decision based on, do I think this is something that has the capability to strongly structure attitudes? And do I have the ability to retrieve the information on the one hand from the survey, and on the other hand from some census or census-like organization that can tell me for a specific unit how many people of each ideal type live there? Okay, so when you think about the fourth step, where we take these ideal type estimates and then we weigh them by the frequency, we add it up, and then we get our estimate for that specific unit. Then we can also think, how do these differences come about that we're then going to see? So if we see that some units are very conservative and others are very liberal, then why does our model come up with that difference? Well, one is that they have a different population structure. Maybe in your model, you see that highly educated people have way more liberal attitudes on a specific question. And if you have a unit that has a lot of highly educated people, then of course, those ideal types, they get way stronger. And so that will lead to a difference in the estimates of these two constituencies. Then it can also stem from the fact that the data you have in the survey, that people in specific units all respond very liberal or very conservative, and that can get that will be partially observed in this like constituency relevant random effect, what was on the slide before called alpha district. And the third way how you can get these differences is that you have different values on these level 2 variables. So the example with presidential vote share, maybe you have a place that had a very large Trump vote, and you have another state that had a very small Trump vote. And that's, of course, then going to translate also into our estimates. So these are like 3 sources that can explain why we get some form of heterogeneity in our estimates. Okay. So I think this might be a perfect point in time to take like roughly a 6-minute break or so. Get yourself a coffee, get yourself a glass of water, and we'll reconvene in 6 minutes. Just waiting. Okay, perfect. Ah, now I see. Oh, I'm muted. Okay, I see there's a question in the chat on the different number of ideal types. Perfect. Thank you very much for providing the reference. Yes, so part of the difference there comes from the number of units also. So the 48 are the states for which there's survey data in Gelman. Then in our case, it's 48 times 26. That's because we have 26 subnational units. And then Hertie and co-authors, they're looking at electoral districts in the UK. And so definitely what you can see when you look at this is that that's, of course, a large number, and that is going to make it somewhat slower. So we're going to see if you just go through this and you estimate your simple, straightforward MRP, then that's not going to be huge. But the very last thing we will see is what happens when we bring in a little bit of machine learning to this. And that actually is slow. And that's, of course, going to be even slower if you're going to go and do this on, let's say, the UK example where you have 1.9 million rows. So there you're definitely going to be taking a hit. And partly, so the second part, no, it's not just because of the number of units. It's also that you might have more or less information. So if you have 3,072 different ideal types within a constituency, that means that you have very, very good data. So that could be that you, for example, have an idea of what people have voted in the past, and you're using that. If you have like 6 or 7 different parties people are voting for, and then you go 1 or 2 elections back, then that can quickly get you up to a high number of ideal types within a constituency. Okay, so what we want to do in the next step is take a quick look at performance. So far, these were just general arguments why MRP could make sense, but let's see some applications to see what that actually means be better than a baseline or so. So the first thing we can do here is look at this figure. This is figure 2, and it comes from this Warshaw-Rodden paper that I mentioned. And what you get here is congressional districts within state, and down here state senate districts. So these are 2 different forms of subnational units they have in their data. And when you go up here, you get the disaggregated mean estimate. So what they had is they had a survey for that state, and then they just take the people from a specific congressional district, and they use that to come up with an estimate. And over here, you see what you get with MRP. And what becomes clear very quickly is that the MRP estimates are much closer to this 45-degree line. And that's what we would want to have, because what they have on the x-axis is the estimate. And what they have on the y-axis is actually a referendum result, because what they're exploiting is that there was a vote on same-sex marriage, and they also have a question on same-sex marriage in that survey. So what they're looking is, can we actually come up with estimates that seem to be closer to what is then like an official measurement of attitudes on same-sex marriage in these congressional districts? And so you see over here that you would have a much smaller mean squared error than you have over here. And then moving down to the lower part of the figure, this is the exact same exercise, but on state Senate districts instead of congressional districts. And here it's even more pronounced. So you see how much spread you can have. Around here, these are state Senate districts that have something between like 40 and 60% in the referendum. But you see on the estimates, it moves around here from like what, 20 up to above 80%. So disaggregation doesn't give you that good results. On the other hand, when we look at MRP, we see that this is doing fairly well. One thing you see here is that it's not perfect. So it's not the case that these estimates are like perfectly correlated with the true outcome. And we also see that we tend to slightly overestimate the support compared to the results we then observe. So you see that a lot of these state Senate districts are below the 45-degree line. But overall, what we see from that is that MRP clearly does much better than disaggregation. And so here I'm coming to another illustration of the power of MRP. And this is now not where we're interested in the subnational. This is a situation where we have a terrible sample. And the question is whether MRP can help us to come up with a better estimate. And so let me tell you a little bit the background to this. So this is a work by Wang, Rothschild, Gelman, and Shirani. And what they do is they exploit that Microsoft runs Xbox, so this like gaming console, and they convince them in 2012 to let them add a survey into the Xbox multiplayer setup. So those of you who actually have an Xbox and know what that is and how it works, apologies if this is a very rough description. But basically, you're 17, you're in the basement of your parents, you want to go and play some shooter game, and you don't want to play against the computer, but you want to play against other people. So you have the possibility to log on, and then you will have this multiplayer setup. When you do so, they were able to have a survey come into your Xbox game, and then you could decide whether you wanted to respond to that survey or not. And they started running the survey at the end of September and went through till November, early November, so about a week before the elections. Now, if you think what happens when you ask people who play Xbox questions, you might not put a lot of faith in the data you generate that way. So when I think about who's actually playing that, I would assume that you have way, way more men than women. I have some hunches on educational structure, on employment status. It's not necessarily data we would like consider reliable. And so what this team does is they run this survey and they run it over this entire time period. And every couple of days, they take the data, they run their MRP model, and they come up with an estimate for the two-party Obama support. So that's what happens when you kick out all the other candidates in individual states. You get other candidates. You might get like a Green candidate or something like that in some states. And you just look at the people that say, I'm going to vote for Obama or I'm going to vote for Romney. and then you compute the two-party Obama share. And what you get here, this like dashed line, is the final official result, what came out. So Obama won the 2012 election against Romney, and that roughly about 52%. Now, what you have here, this like green dashed line, that's here, it's not so easy to see. This is the average of a lot of published polls back then from pollster.com. So the idea is every single poll exhibits noise, but if we take a bunch of polls and average over these polls, we should come up with a pretty good estimate. So you can think of this as like the overall estimate of the wisdom of polling. And then you get this red line together with its uncertainty, and that is the MRP adjusted Xbox estimate. So that's the MRP model that Wang et al. Ran on this Xbox data. And so you see this movement here. And then interestingly enough, about 3 weeks before the elections, this jumps up. And until the end, it is pretty much covering the final true result. Now, I bring this example because on the one hand, it might show you what kind of fairly special data can still be used in a productive way if you have a good model that you put it into. Also, because this is an example that is again and again brought up to illustrate the power of MRP. But at the same time, I would also caution because we have to take into account that these are not pre-registered studies. We don't know how many other people used some random data, ran MRP, got completely senseless results, and then, of course, didn't publish it. So this would be a classic example for the file drawer problem, where what we see ending up published in papers is, of course, not representative of all studies that were carried out. So you can think of this maybe more like a prototype illustration that it may work. What it doesn't tell us is whether it always works or what the conditions are that MRP will help you with a problematic sample. Okay, so that's essentially all on the basic Mr. P model that we want to talk today before we then go into the lab and actually estimate some of these models and see how we do that. Just going to wait a little moment in case there's any final question on MRP before we're going to look at the extensions. Okay, I don't see any question popping up, and otherwise we'll have time later to get into it. So Mr. P used to be this single guy, got very famous, was often used, but there's actually more. And what has happened is that, of course, people have realized, hey, there's applications where Mr. P is not like working optimally, or there's actually things we might do better. And so I'm going to discuss here two examples. One is Mrs. P, and the other is Auto MRP. But these are not all of the extensions that are out there. There's also others. So for example, Selben Munzert, the quote you saw earlier, this 2011 paper from Political Analysis, they're dealing with a problem where you have so many subnational units you care for, in their case, it's electoral districts in Germany, that you will have a lot of districts for which you do not have a single respondent in your survey. And what they work there on is a way how you can deal with such a high number of subnational units. Then there's something called Deep Interactions by Gitza and Gelman, which is something that you could be interested in if you really care more about dissecting public opinion and you really want to come down into very specific groups. The basic idea is think about this like interactions of random effects. So you might have this like female and male realization, and we said it is constant. But you could also say, well, maybe I want that gender difference I'm picking up, that can vary across ethnic groups, because maybe you have an idea that for African Americans, there might be a very small gender gap, but for Caucasians, that should be very large or something like that. So if you want to get into situations or model something like that, then that would be the Deep Interactions paper by Kitza and Gelman. I see there is a question now in the chat. Are there any limits pertaining to the number of ideal types depending on the number of empty cells? So the nice thing is that when we set this up, we don't think in terms of empty cells, because we will always be able to come up with an estimate, because we're always going to have people in the individual categories. We might not have this like perfect combination. So we will have young people, we will have people with university degrees. Even if we don't have a young person with a university degree, because we're using a model, we can still come up with an estimate for that. So empty cells is something that is specifically related to traditional post-ratification, where you don't have a model and you just take all the people of a specific type, and then you take the average value on that item, and that's your estimate for that type. But we don't do that. We have this elaborate model, and that model can deal with it. Now, there's not a lot of work that tries to think about, is there an optimal number of categories? Should we maybe do the age in 5-year steps rather than these like large 15 or 20-year chunks? Of course, at the very end, when we see what machine learning can do, their part of this question can go in, because you don't actually deal that directly with it, or you could think of ways to deal not that directly with it. But often it's also going to be just a matter of how much data can you get from a third-party source, often the Census Bureau, that is going to give you these breakdowns. And so if you go to a Census Bureau and you say, I want to have it in 5-year brackets, they're going to be much more hesitant to give you a lot of other combined data, because we then really get into a situation where you might have perfectly identifiable information. Does that mean that if we have a lot of ideal types that we will just get a value super close for? Yes, so here it's important that we keep in mind what we saw before, where we were just looking at partial pooling, was a situation where we just had a random effect for these units, and we didn't distinguish individuals in any other way. The only thing we knew was, what did an individual say on this left-right scale? Where does an individual live? That was all the information we had. But here we're in a situation where we also take into account education, gender, potentially employment status, potentially ethnic group, or something like that. So the individual groups are usually not that small, because it's not the size of the ideal type that we worry here when it's about the realization of the random effect. It's the number of people in a specific category. So if you do these age categories, and you were going down to maybe like an age category for every year, and you have like, what is it? If we start at 18 and we assume the oldest person is 100 years old, then we have 83 different categories. There we will definitely see that a lot of these categories have very few people, and yes, that would pull them there. But usually if you're working with these more conventional categories, that might be something like we saw before, where you split age into 4 groups, then you wouldn't run into, or unlikely into, a situation where it gets pulled very close to the grand mean. And if that happens, then that would be a consequence of a lot of uncertainty within your group. Remember, it's not just the sample size of a specific category that goes into these relative weights. It's also how much noise is in the responses. So if you then have a category that seems to be all over the place in terms of attitudes, it also makes sense that we move that closer to the grand mean, because we don't have a lot of faith in that specific local estimate that we have there. Okay, so the first,
sorry, Dan,
yeah.
sorry to interrupt. There's another question. You said that because of low response rates, random sampling has generally run into problems. But when do we need to use MRP? As in, when can we live with a YouGov sample that is not always completely random, and when can we not?
Yeah. So as said, unfortunately, there's no easy indicators for that. So we're not in a world where there's like a single number you can look at, or where there's like some kind of 0.05 rule. One thing that you might want to do, but this also depends on how important is this specific step. But let's say you're working on a larger project, this is your dissertation, or you're doing like a paper and you think this actually has a lot of juice and is going to go far, then it's probably worth to be as thorough as possible. And so one thing might be that at some point, let's say you already started and you're using disaggregation. Now you might wonder, do I need to bother? Do I not need to bother? Well, when you're looking at the level 2, all we know is that you're always getting really much, much better by using MRP. Now, if you only care about national averages, and that might be where the question is coming from, because they refer to YouGov that usually has fairly okay samples, then one thing you could do is you could, for example, just check and see how much difference does it do. If I have a sample and I look at the sample mean and then I do MRP and I see a huge difference, I will always go with the MRP estimate. If you run an MRP model and you see the difference is very minimal, then one thing you could do is actually add that analysis, put it somewhere in the appendix, and then tell readers in a footnote that you've actually also explored this, but it seems to have minimal differences, so it seems to be working fine. But that would be on the national case. When you're looking at subnational units and trying to come up with these estimates, you will almost surely end up in a situation where MRP is more precise than just the sample the way you have it. The only reason why I'm saying guaranteed, not saying guaranteed always, is I'm sure sooner or later there's going to be some weird data example where in one case it actually does not hold. But as a rule of thumb, you would want to use MRP when you look at the level, at the constituency level. Did I miss another question, Philip?
No, that's all.
Okay, perfect. So this level 1 improvement is based on a paper that came out of another paper where the authors used MRP and were a little bit frustrated because the problem they had was that when you look at your survey data and you're thinking about, hey, what's a good response model? So what should I put in? Should I actually put in a random effect for gender? Should I put in one for age and so on? They actually realized that they have a lot of variables in the survey data that are good in predicting attitudes. So you can like really come up with good estimates, but you don't get them from the Census Bureau. So part of that might be data protection, part might be political, that it's data that is not collected. So a simple example is political party. There is no collection of individual party preferences by the state in Switzerland. Now, there's a lot of reasons why this is a good idea, that the state does not ask me about my opinion or partisan preferences and record that on an individual level and collect that data. On the other hand, if we were very myopic and only care about MRP, of course we would want the state to collect that. Because if you think about it, many attitudes that we want to model, you could do a better job if you could use partisan identification of the individuals. But if you have a party variable in the survey, then you're like, oh, great. You put that in, you see, oh yeah, that actually works fairly nice. But if you don't have it in the census data, you can't do this like last step of MRP because you just don't know how many young women with a university degree living in an urban area also feel close to a center-right liberal party. Now, we were facing this issue somewhat frustrated, started thinking about how can you deal with it. And so the difficulty here is really that at the end of the day, the technical problem emerges from the fact that we're using a probit model. So the situation we have is that the ideal types that we use usually require census data, but the census will not collect all information that we might want to use. And so we're going to look at a very stylized example and think about a couple of things here. So we have this again, this like men, women, low education, high education. And what we need to do MRP is we need these numbers here. I need to know there's 40% of the total population that are male, low education. There's 20% men, high education, 20% women, low education, 20% women, high education. So this is a weird society because it has a strong gender imbalance. Now, the census gives you, technically, this is a joint distribution because it gives you the frequency of more than one variable. That's why it's joint. And what you see here in the outside part, that would be the distribution of the individual variable, not taking into account how it breaks down by the other categories. Now, sometimes there's a way to get, so this is known as the marginal distribution because it just is what you have in the margins. Sometimes there's actually a way to get this information not from the census. So going back to the motivating case in terms of party preferences, I might not get from the census this breakdown for a specific ideal type and then which party they prefer. But every 4 years, there's elections, and for every single municipality, I get the perfect breakdown of votes submitted, and I can see how many votes did which party receive. I can aggregate that to the cantonal level, and in that sense, the marginal party ID, or in this case, what I'm really looking at is expressed party preferences in a vote. That information is there. But what I don't know now is how many from this marginal, how does this distribute across these other types? So the problem is I have a joint, I have a marginal, and how can I still use this? Now, take a step back and forget that we usually have this set up where it's a probit. So I just wrote capital F, just saying there's a function that we apply. Now, what we usually do is we have the number of people that belong to a specific ideal type that are part of constituency C. Then we add all these realizations of random effects together. So you have here, we're summing over J and we're summing over M. And then we divide by all people in C. And what we would like to do is essentially move this function out here. Why would we want to do that? Because if you look at this expression, then you don't need the joint distribution, because here we're just adding things up. I don't need to know how many men are also highly educated and have a university degree and self-identify with the Social Democratic Party, because this is all additive. So it doesn't matter. And over here, it doesn't matter if F, for example, is an identity function. But it will matter if we have a probit here. So for those of you who just recently maybe had a class on binary models, you might remember that the marginal effect depends on where a specific observation is. going from like an income level of 50,000 euros to 60,000 euros has a different effect depending on whether you have a low probability, a medium probability, or a high probability, because we're on this S curve, and adding a constant on the latent is not going to cause the same difference in predicted probability depending on where you are. And so that is what gets us in trouble in MRP. And that's why we really need the individual combinations of all these ideal types. Otherwise, we could just be adding over all these and it would work out fine. So as said, if f is the identity function, then that equality holds. But if f is a logit or a probit or so, this is not going to hold. So this equality would be wrong. And that means that we actually do need to know, okay, so now I'm going to add this realization of a random effect, but I need to know, am I now adding it to a young man with university degree, or is it a young woman with university degree? And so that is actually going to get me into trouble. So that was very frustrating. But then the first idea coming here was like, well, you know, do we really need logit and probit? Aren't we like past that? What happens if we just say, we're going to run essentially the equivalent of like a simple linear model on a binary outcome, because then these problems go away. So we quickly explored that. Turns out that doesn't do well. And the reason it doesn't do well is, of course, because of the basics. When you're told why you want to use a probit or a logit, then you go through these various things. So you have built-in heteroscedasticity if you just run OLS, but we might not care about that. But one thing we get is out of bound predictions. That's going to happen, of course, here. And so we evaluated that, but you're just not performing well. So overall, you really have higher mean squared errors. And the reason for that is that you get these like fairly extreme estimates for some groups. Okay, so what else can we do? Well, one thing is that maybe there's a way when we have a marginal and we have a joint distribution to somehow integrate that data. And that is what we're going to do in the next step. And so here you see again the stringent data requirements, why you not always get that full joint. So it can be because you're really like not getting it, not because it doesn't exist, because they don't want to share it with you. That's one possibility for data privacy, or because it's data that is actually not being collected by a national agency. So down here specifically, you have again this Warschau and Rotten piece 2012, and there's a footnote in here where they specifically say, because Census Fact Finder, that's this online tool where you can download the census information in the US, does not include age breakdowns for each race, gender, education subgroup. We are not able to control for respondents' age in our model. So that's just a hard boundary you're going to face. And the consequence for them was they didn't use age. Now, remember, they're analyzing same-sex marriage attitudes. And one thing we know is that same-sex marriage attitudes, that they differ strongly across cohorts. So this is, of course, painful when you realize we're not getting at the census information, so we can't use that variable. As mentioned before, an alternative would be like this linear link function, just like pretending that you can do that. We tried that. That was Midwest 2013. That doesn't work at all. Now, the alternative, and that's why we call it Mr. P's better half, because it's Mrs. P, it's multi-level regression with synthetic post-ratification. And why synthetic? Because we will make up a new joint distribution that is synthetic. It's not the real joint distribution, it's an approximation. There's two versions of it. There's the simple Mrs. P, and what we're going to do is we're just going to assume that that one variable, for example, party ID, that I also want to use, that's orthogonal to all the other variables. So if I observe in a specific canton that 20% of the people are voting for Social Democrats, then I will just assume that in each ideal type, 20% in that unit will vote for Social Democrats. And of course, we know that's not true. We know that certain age groups have a higher propensity to vote for Social Democrats and so on and so forth. So there's another approach called elaborate Mrs. P, where we use the survey data that we're already using for the MRP response model. And we're trying to exploit there that we can learn about the correlation of age and party preferences and use that when we generate the synthetic joint distribution. As it turns out, that usually doesn't lead to a huge difference, simple Mrs. P or elaborate Mrs. P. And what I want to show you here is just a replication of the Warshaw and Rodden data with Mrs. P. So we, in that paper, do stuff with Swiss data, but then we also go and we use their data because they make everything available. They had like fantastic code. It was very easy for us to replicate it and then to see, hey, is this idea, does this actually work? Do we really perform better? And so remember, they always make the comparison between disaggregation and Mr. P. And what we're doing here, and I'm going to zoom in a little bit, is we're taking their data, and you see you have these like tiny gray plus signs here. Those are the individual disaggregation results. And then you get these red triangles. That's the MRP estimate by Warshaw-Rodden. And the blue dots, that's what we get when we actually download just the age distribution in these different Senate districts, and then merge that, combine that with the other census information, and pretend that this new joint distribution would be the true joint distribution. We know it's not perfect, but it's an approximation. And as you can see, it actually does much better. If you look at the mean squared area, you see disaggregation, you get 0.02. With MRP, you get 0.014. And with Mrs. P, you actually get down to 0.008. So if you think in terms of PRE, proportional reduction of error, then the difference from disaggregation to MRP is actually way smaller than the difference from MRP to Mrs. P. Disaggregation error goes down by about a third if you use MRP. But if you use Mrs. P over MRP, you cut the error almost again in half. So this is, of course, a really nice illustration that there are situations where you should strongly consider to actually rely on a synthetic joint distribution and use Mrs. P, who's Mr. P's better half. To be fair, this was, of course, a very good example to illustrate the strengths of Mrs. P. Why? Because the one variable that the original authors had to exclude, it's not that they decided themselves, oh, we don't want age. It's that they didn't get it on that level with the others, so they couldn't use it, was age. And at the same time, age is a super, super strong predictor in that time period in the US for same-sex marriage. So it's only worth going through this, of course, if it's a variable you could otherwise not use that is a really strong predictor of specific attitudes. So that's the first extension on level 1. So an extension, if you have a problem with configuring your response model with the individual level variables. Okay. And then the second improvement that I'm quickly going to mention before we head for the break is actually joint work with Philip, who's also here, and Reto Wüst. And this is something that probably doesn't come as a surprise, but we've all experienced the machine learning revolution or emergence in the social sciences. And then, of course, didn't take long that people started wondering, hey, you know, this MRP stuff works well, but what happens when we actually use some of these like basic tools from machine learning? Because if you think about it, it's a classification problem that you're facing. You have data, you know what people tell you on the survey response, you have a bunch of features, you know, age, education, and so on. And so maybe we can do better if we rely on some of these simple tools than if we just like slavishly go and apply our standard response model. And so specifically here, I want to highlight this point, because if you think about this from a machine learning angle, then one thing you will have noted is that these random effects, they, of course, all have kind of a built-in regularization. Yeah, they're already like a little bit shrunk towards zero, these like group differences that would emerge. That's a little bit like the lasso estimate where your like betas are a little bit pulled back. But there's one thing in an MRP model that doesn't have any form of bounds or regularization that is applying, and that is the level 2 variables that you're integrating. So that's why I'm highlighting this part again in red. You've already seen the entire slide before. It's really just to remind us that in many of these MRP models, we're adding variables at the context level, like presidential vote share or share of German speakers, and there's nothing in there that protects you from overfitting. That in itself might not be too worrisome, but take that together with past work that illustrates that for the performance of MRP estimates, the level 2 variables and the good selection of level 2 variables can be really decisive for the quality of the estimate. That's part of the Warshaw and Rotten 2012 paper. Now, in light of that, we might start to worry and say, oh, okay, so we have a model, we have one part that doesn't have any kind of protection against overfitting, and we also know that that's often a very important part for the performance of our models. So we should probably do something about it. Now, first step is you go and you look what the big names in this field have written on how to come up with the right set of level 2 explanatory factors or features. So you look at the Park et al., the Enns and Koch, Lax and Phillips, Warshaw, Rotten, Gitza, Gelman, Tosanovich, Warshaw, Eggers, Lauderdale. You look through all these papers, great papers, all illustrating how you can use MRP in various different settings, showing how you can overcome various difficulties. But the one thing that is not discussed in any of these papers in great detail is how did these authors decide which level 2 variable comes into the response model and which doesn't. And so that is where you see how it can be valuable to maybe use some simple tools from machine learning and not just you yourself sitting at your computer and being like, should I maybe add cantonal level education expenditure per capita, or should I not add it? Well, there's probably better ways to deal with this question than just like pure gut feeling. So it seems like there's no systematic selection. Now you start thinking, should I maximize the model fit? But we all know if you just throw in a lot of stuff, then in sample, your model fit is always going to go up or stay the same. Shall I do it theoretically? Shall I think what are context level factors that should be correlated? But that's also not that straightforward. So where do we go from here? If you don't select any, you're going to be underfitting and your model estimates are not going to be that good. If you select too many and also ones that shouldn't necessarily be there, then you have overfitting. So auto MRP in like 2 slides. First, what we do is we take 5 very simple classifiers: best subset, lasso, PCA, gradient boosting, and support vector machine. In principle, you can add additional classifiers if you have something else that you want to add to it. And then what we do is, because we have these different estimators or classifiers, and they will come up with different estimates, we then use ensemble Bayesian model averaging to take all these 5 back together and come up with one final set of estimates. And so what this does is you can just provide a list of potential level 2 factors that you want to include into your model, and you rely on machine learning to come up with maybe not the perfect model, but something that is closer towards an optimal model than what you would come up with if you did it yourself. What you see here is the performance. This is if you just throw in all variables. Of course, you're terribly overfitting. You see that you get a fairly high mean squared error. Then this is the support vector machine best subset loss. So this is an empty model where you're underfitting. This is PCA, principal component analysis. This is the baseline. We're doing this on a data set that has a lot of outcomes that other people have already used to evaluate MRP models. Then gradient boosting, and you see our combined estimate then cuts by 12% the mean squared error versus the baseline. The other thing you can do is also compare auto MRP to two other approaches that bring machine learning elements and MRP together. That would be first here, again, the baseline, just standard MRP. Then here you have BARP, here you have SRP, and then here you get auto MRP. Okay, so to conclude, MRP is in its beginning a model-based alternative to just pure raking or post-ratification. It allows you to generate very good estimates for small areas. It comes with costs. There's no free lunch. So you need much more data. You suddenly actually need census information, and there's some complexity to it. And the other problem that you might have not yet realized is that it's not observation specific, but outcome specific. So in the old world, if you just do raking, then you get each observation and you create a weight for that observation. But that doesn't change over any survey response. So you do it once, and then you can just analyze your entire survey with these like weighted outcomes. But with MRP, we always have to do a new model for every outcome we analyze. So it's not data set specific, it's item specific. So that is much more work, but you also end up getting better estimates. A question that will not go away, and MRP is not a magical solution that will always help, is how can we handle non-probability surveys? This question, this will be around for some time. Right now, we don't have a perfect setup. Let's see in 2-3 years if that slide would look slightly different. And so what I want to do in the lab is run through an example of MRP, then do some MSSP, and then also show you an illustration of auto MRP. Now, before we do a larger break, quick question, Philip, have I missed any questions?
Yeah, there's one more question, 2 more questions. So the first one is, if we have 26 areas within a national sample, then presumably we have less risk of a 0 cell and easier to do partial pooling than say with 632 UK units.
Yes, but as you saw before in the Warsaw-Rodden example, they have no single empty cell. Yeah, so I'm going to go back to their very nice plot that we were looking at when we talked about performance. They don't have any empty cell problems. Nevertheless, MRP is much, much better than disaggregation. So even if you don't have empty cells, you still want to be using MRP. You are still getting better estimates over here than you see over here.
Yeah, and there's one more question on whether it's possible to use MRP in a causal inference setting.
Yes, it depends what you exactly mean by that. So one thing you could imagine is that you run MRP within an experiment. And actually there's work by Lauren Kennedy, a former postdoc at Columbia, who's now at the stats department of Monash University in Australia. If you Google Lauren Kennedy, causal inference, MRP, you should find her working paper. It's fairly technical, but that's exactly what she's working on. How can we actually come up and work out conditions and issues with MRP when we're integrating that into a setting where we might have an experiment or some other clearly identifiable change that is exogenous. Okay. Did I get all questions?
Yeah.
Perfect, good. At this point, maybe Olga, what's the timeline? Is this the 15-minute break?
Yes, if you want to break now, it's a good time. Yeah, great.
Okay, so we'll do 15 minutes. My clock says 11:08, so we're going to be back at 11:23.
There are many challenges of modern governance that can only be tackled with data. So we need data scientists and data analysts who have the tools to do so. But we also need data scientists and analysts who understand public policy, who understand the governance of data.
Data science for public policy is important because we think that's the only way to answer complex questions that are facing society at the moment.
Mainly because nowadays we can no longer talk about policies without thinking about how AI and data affects our lives. I think the decisions to create the new Masters of Data Science for Public Policy, it's a natural progression of the school's mission to train and educate the next generations of leaders and policymakers.
So why is it important? It's because, everything that you can think of, the climate, the crisis of democracy, the pandemic, the coming pandemics, just fairness, justice, the ancient problems of humanity, but they all mix together.
And for me personally, I'm thinking about that I want to leave the world a better place for my young daughter. And that's what is motivating me to work on that. Data science enables policymakers to think through different channels.
So that's why I think it's really important to do this kind of thing in a school of governance, because you have an opportunity to try to make the government problem itself better.
So we've designed a program in 3 pillars: public policy and governance pillar, a data science pillar, and what we call a solutions engineering pillar.
Integrating this with public policy and applications of public policy in law, economics, leadership, management.
And when you put the two together, it's basically using the powerful framework that data science offers to us and for decision-making process within the government.
Students should and can look forward to development of cutting-edge techniques in machine learning, in deep learning, natural language processing, computer vision, but also application of those techniques to public policy. And then finally bring this all together into development of solutions that can be presented to policymakers.
What makes the program unique is the way our students will study here. They will study alongside students of public policy, alongside students of international affairs. So many of them will explore, will grapple with similar problems, will search for similar solutions, but will do so from different perspectives. It's the Hertie School's mission to train tomorrow's policy leaders, policymakers, and policy analysts for our societies, for public policy, for the common good.
I am a sociologist and I specialize in development studies, which is more about how countries develop and why some don't. And so I think my thinking goes more about development of third world countries like Africa, like countries in Africa. And so I've always been thinking about that over time. My master's degree was on corruption, which was like a big thing in Nigeria, and I wanted to see how that affected the development of the country. My PhD topic is about international migration, basically how international migration is like a source of inequality, and people seems to see international migration as a sort of opportunity to learn around the world. But I was intrigued by the fact that some people school abroad, and when they return to Nigeria, they don't get jobs. Though it started like from an intuitive, it started from my intuition, like it's possible that people who go abroad and come back are not being able to deploy their skills, because we find out that a lot of people that I know go study abroad, but the skills they learn is not being used, or we can't seem to see it in the development of the country. So it was an intuitive thing, like, where are the skills? Where do these skills lie? I'm not too sure I want to stay too much in academics. I'm not too sure at the moment, because I feel like there's this passion for working in think tanks and working to support societies. I don't know how that would work with working in the academics yet, but I think I would tilt towards helping. We don't have too much think tanks in Nigeria, and those that we have do not have the capacity. So hoping to go back at some point and develop something really nice that can help to think about researching into key issues that affect development in Nigeria. And if my time being into academics is going to distort that, I think I would rather go for that and see how we can support institutions in Nigeria to think about research, technology, and use of research and technology to develop new ideas to solve Africans or Nigerians' problems. So I would go for that first before thinking about furthering academic endeavors. So yeah. Script is very outstanding for me because I come from the part of the world where there is a lot of problems that is being caused by the changes in the international global order. And then script seems to not just talk about the problems in international global order, but it also talks about how it affects where people like us come from and how politics is changing how people think, and how the definition of liberalism, the definition of freedom, it's not really clear for most people. And if I think also if I want to be very clear about this, it's the problems of liberalism these days is you chase after one opportunity, and that opportunity perhaps will create a disadvantage for you in other areas. And so it's if you're pursuing one area that is great, it also might lead you to suffer in other areas. And these are the things I think scripts really want to catch up to, what are the contestations, what are the things that are not clear about liberalism, and then maybe if we, at the end of the 3-4 years, we can answer some of these questions and tell people and tell the world this is where liberalism is going, and this is what we think about liberalism and the liberal script in general. So that's what gave me interest in the script programming. Berlin combines for me the perfect place I would like to be, intellectually, professionally, and personally. There's so much to see here if you really want to see. So you have a lot of schools, a lot of things happening intellectually, and it's just now depends on myself to take advantage of these opportunities, but it's all there, and it's just one of the best places to be.
Okay, welcome back. Hope you had a nice break. What we want to do in the remaining roughly 90 minutes is go through specific code examples. And the idea behind this is that you kind of have a template and that you know how you would apply that if you're going to use it in your own work. And so the data structure might look slightly different, but you should be able to adapt the code here such that you can then use it for yourself. So just a note, there's a bunch of libraries here. The Swiss MRP, you don't necessarily need that. I just want to have it to call up a specific help file to show something, but we're not going to use it otherwise. So I'm going to start here and load in this data set called mineretb.dta is a stata data set. What it is data that is similar, looks like the data in the post-vote survey in Switzerland after it was voted on the initiative to ban minarets in 2009. And we're going to use this data. We're going to look at estimates we will come up with in that sample, and then we're going to apply MRP and see how that works out. So if you look into it, then you're going to see that we have here a bunch of variables. We have one called minaret, then we have one called Kriegsmachtverbot. That was another issue that was voted on that weekend, banning the export of military products. Then you see we already have categories, female, age groups, and not individual age, but age group, then canton number, a numerical identifier for the canton in which somebody lives. Then here you have the abbreviation, education groups, party preferences, the region, German, another cantonal ID variable. And then here you see this is education expenditure per capita, then a variable indicating urbanization, and the joint share of votes for left parties in a specific canton in 2011. So what I'm first going to do is just look at the raw data. So let's see what we have here when we look at the breakdown. Okay, so we see we get 351 zeros, those are no's, and 330 ones. Overall, we have about 1,000 observations, but you see that only about 680 people indicate in this survey what they voted or didn't vote. So what I'm going to do is I'm going to kick out all the observations where we don't have a yes or a no. And now let's go and take a look at the relative shares of these two outcomes. So what you see is here, essentially, the average, which would be your sample-based estimate. And so,
Lucas, so can I just quickly interrupt? There's someone who's asking if you can change the background to a light background in RStudio.
Yes. Like this. Okay, so what we have here is then this estimate, and we see that based on this sample, you would assume that there's a large minority, but still a minority of like what, 48.5% people supporting this minaret ban. So let me fast forward to give you the punchline. The initiative passed with 57.5% yes vote at the ballot box. So now the question, of course, is this just like tough luck? Is it just that this sample somehow is not perfect and can we model our way out of it? Or is this maybe an example of social desirability bias where people kind of wanted to ban minarets, but didn't want to say that in an interview situation? That was back then in the first shock, a likely explanation that was used. So what we're going to do is we're going to estimate a very, very simple model here. This is not the
Sorry, just again, one more interruption. Can we also make the font size a bit bigger?
Yep. Does this work?
I think that's good.
Can everybody see and read it? Gonna wait a second just to be sure.
Yeah, I think it's fine. There's a small delay on YouTube, but I don't know if we can do anything about that.
Okay. Good. So what we're going to do is set up a very, very simple MRP model. And what this is going to do is break down this survey response on Minaret. We're going to have a constant, and then we're going to have a random effect. And this is how we specify it when we estimate the Glimmer model for the variable female, which is just a binary gender indicator. Then we have a random effect for age groups. We have 4 of them. A random effect for education, we have 6, and the random effect for the cantons. And we're going to specify that as a pro-bit model. So I'm going to do that. And now we're going to take a quick look at this output. So A, you're going to get a warning message boundary, and we're going to take a quick look at this first part here. So what this block gives you in the output of a multi-level model is these estimates for the variances of these random effects. Down here, you see the constant. So this is this kind of standard output, from various regression models. But we're going to first focus up here, and you're going to note 2 things. Now, we're running this with 680 observations, which is a little bit on the low side. And what happens, and this is something that happens, unfortunately, fairly frequently when you're working with Glimmer, is that when the differences across certain categories of a random effect are very, very small, Glimmer tends to fall into the 0 trap. So what happens here is that it's telling us the variance across cantons of the random effect realizations is 0, meaning the realization for each cantonal random effect in this model now is 0, and the same happens for female. Now, this is somewhat unfortunate because already now we know we will not be picking up cross-cantonal cultural aspects or something like that. Nothing of that is going to come in, and men and women will not differ in our model. I'm nevertheless going to just work through every single step as if there were numbers there. In an applied setting, if this is the situation I would run into, then I would at this point probably switch over into a Bayesian setup where I wouldn't have this issue and set it up in Stan.
There's also a question on the number of observations. So whether you could impute the missing values on the dependent variable.
On the outcome variable, yes, we could think about whether it would make sense to first go and impute that. You could definitely do it. I'm trying to figure out if I'm aware of anybody that has tried to evaluate and come up with trade-offs of imputing in MRP models. I don't think that there is any such work right now out there. I'm at least not aware of looking at when that is most beneficial or least. But yes, you could go and try that. Okay, now the first thing I need to do is I need to get these random effects out of the model, because remember, we're then going to start building for each ideal type. We're going to build that estimate. So I need to know what's the realization of the random effect for women? What's the realization of the random effect for men? So what I'm going to do is I'm going to create these 4 objects here, RE dot, and then the variable name that gives us the categories. So if you look at this, and I'm going to look at this object right away, then you see this is the random effect realization for men and for women. And as we saw before here, they're both 0. I can do that for age groups. And when I do it for age groups, you're going to see how we get for the youngest group minus 0.02, then something similar for the second group, then for the third group plus 0.005, and for the oldest group minus 0.01. So that tells you a little bit which age group on average is more in favor of the ban of minarets and less. Then we're going to do the same for education and Canton. So now we have each of these random effects saved. Now what we need to do is we start to build together our ideal types. We're going to have 48 ideal types here because we have 2 for gender, 6 for education, and then 4 for age groups. And what I'm going to do is I'm going to show you the census object. So if you load this R data that is also available where the code is available on the slides, then we're going to check up here, census object. Then what you see is this kind of huge matrix. And let's count the number of columns. We have 26 columns and we have 10 emitted rows. We're at 38. We have 48 rows and 26 columns. So what this is the number of each ideal type in each canton based on old census information. We still don't know now exactly, well, what is this group where we have 10,742 individuals in the canton of Zurich? I happen to know that the number 1 is the canton of Zurich. Well, that's why I said you don't need the Swiss MRP package, but I need it because we want to take a quick look here at this help file, because that's where I sucked the data out. And what you see is that these rows conform to a specific logic. So row 1 is the first education category, the first age category, and the first gender category. So that's lowest level of education, lowest age group, men. This is lowest education group, lowest age category, women, and so on and so forth. So you see back here, we're doing 1, 2, 1, 2, 1, 2. Here we're doing 1, 1, 2, 2, 3, 3. And here we're doing 8 1s, 8 2s until the end. Because what we're now going to do is we're now going to create a vector for the realization of the gender random effect, and it's going to have 48 elements, and we want that the first element is for men, the second element is for women, the third element is for men, the fourth element is for women, and so on and so forth.
Lucas, so, quick question.
Yeah.
2 quick questions actually. First one on the model. So whether that's just controlling for confounders such as age, education, and so on. So whether that's what the model is doing, model 1.
I think it's important at this point to highlight we're trying to come up with an estimate, and we're not trying to estimate something like a causal model of anything. Actually, if we had, and we're going to do that very soon, if we knew how places used to vote on other right populist issues, then we're going to use that. Like causally, it doesn't make sense to somehow use right populist voting behavior a year before to explain current year. So like the causality is completely unclear. But we don't care because we're in a measurement step, meaning things that are correlated are valuable to us for the measurement step. The direction or the causality is not relevant in this setup. So if I want to know what are the difference between education groups, I wouldn't be running this kind of MRP model. That's not the purpose. You said there was a second question.
Yeah, so the second question is whether the number in brackets is the reference group. And I think that's in the code when you go down a little bit.
The number in brackets here.
Yeah, in the
No, that's just because the way how these objects are stored when you run a Glimmer model. So look, I'll just now like execute that one part of the code that is highlighted. So ranf model $1 female, then you see that's this. And so I think we can do it like this is vector, and then we get false. And when I do bracket 1, then what I do have is something that is a vector. That's the only reason. So it's not reference group or anything. It's just making sure that I get the random effects out as a vector. Okay. Now what I want to do, I want to create for each of these random effects a vector of 48 elements that always at the right point has the right realization. So for the gender random effect we saw, it's always male, female, male, female, male, female. So that's kind of easy because I can just say, hey, take that one that exists for men, women, and repeat it 24 times and call that female.re. Now, age is a little bit more difficult, no, because I have 1, 1, 2, 2, 3, 3, 4, 4, and then I start again, 1, 1, 2, 2, 3, 3, 4, 4. And I do that overall 6 times. So in a first step, what I do is I use the Kronecker product. So that might bring up some bad memories from high school math. I'm just going to execute this inner part that you see what happens. When I provide 2 arguments, it's like outer multiplication of the age group. So remember, that's going to be 4 elements for the 4 groups and just a vector that has 2 1s. Then what I get back is this. And if you look closely, you realize, it's repeating the first 2 elements. Then it's repeating the second element twice. Then it's repeating the third element and then the fourth element. So now I have exactly this 1, 1, 2, 2, 3, 3, 4, 4 structure. And now I just need to say, repeat that 6 times. And the last one we have is education. And education, we just have 1 to 6, but it's 1, 1, 1, 1, 1, 1, 1, 1, 1, and then 8 times 2, then 8 times 3, and so on. So here we can just use the Kronecker product on the random effect realizations of education. And when you now look at this element, you will see that the first 8 elements are identical. Yeah, they're all identical. Then the second 8 elements are all identical, and so on and so forth. Now, this is really the part of MRP that essentially has nothing to do with stats. It's like bookkeeping. It's cumbersome and it can like confuse, but this is really just figuring out how to get the right information in the right slot that in the end we can easily combine these things. And I'll show you now why setting it up this way is so nice. Because now we have for each random effect a vector of 48 elements, and in every row we have the correct realization according to this structure. And I'm of course choosing this structure because I know my census data has exactly this structure. And now what I can do is I can just go and sum over the rows after I C-bind these 3 vectors. So I'm creating now an object that is just going to have 48 elements, and it's just adding up the realizations of the random effect. Remember, we also had a constant in the model. That also needs to be added. Nicely enough, that thing is constant for every observation, so we can just in the end slap it on to this object ind.re. So what we now have is a vector with 48 elements, and this is the score on the latent variable of our binary model for each of the 48 ideal types. But ultimately, where we want to go is 48 ideal types in 26 different cantons. So what I'm now going to generate is a very, very long vector with 1248 slots, and I'm going to call it ylat1. So ylat for y latent, and 1 because it's the one belonging to model 1. And now I'm going to run through this loop, and I'm going to go through for each canton, because essentially observations 1 to 48 on this ylat1 vector, they belong to canton number 1. Observations 49 to 96 are the 48 ideal types on canton 2, and so on and so forth. So what this code does is it goes through, it figures first out here. This is just a complicated way of getting the first row for a specific canton in that object, and B is the last one. And then I kind of slide to that part of the vector, and I put in the 48 ideal types we've generated up here. But I remember that I also need to add the realization of the cantonal random effect. Now what I have is a vector with 1248 scores on that latent variable. So for every ideal type in every canton, I have a model-based linear projection. But we need to remember that we estimated a probit model. So when we're translating this to predict the probabilities, we need to shove it through the cumulative normal distribution, which is done with P norm. I do that, and I call that element P1, predict the probabilities of model 1. And now the only thing we need to do is we need to take the census object that we saw before, that was this matrix that had 26 columns and 48 rows. And I'm also going to, instead of use it as a matrix, I'm going to create a long vector with 1248 elements, such that I have the exact same vector like to predict the probabilities that has the number of such ideal types in their specific location. I'm going to do this here. And now the only thing I need to do is I need to multiply, because now I'm going to go for a national estimate. I'm going to multiply the A vector, which is 1248 elements long and has the number of people that belong to that specific group. I'm going to multiply that with their specific estimate, and then I'm going to divide by the sum of all people. And that's going to give me the national level estimate. Boom. National level estimate, 58.01%. Remember, ballot result officially that Sunday afternoon after counting, 57.5%. So you have survey data. The survey raw data, when you just use it like you would traditionally use survey data, tells you 48, 49%, which is far off from the actual outcome. You use MRP on it, boom, you get an estimate extremely close to the actual true value. Okay. So this is when I hope that you're all in full awe in front of your screens and fascinated. If you start digging down into the data, what you're going to see is here the education category is doing a lot of the heavy lifting. It's one of these classic problems. So this is actually a phone-based survey. You usually have a strong self-selection that highly educated people participate way more in such surveys than less educated people. And when you look at the support for banning minarets, then you will see that people with little education exhibit very strong support, while highly educated people were strongly against it. So it's the perfect recipe for disaster. You get too many of one group, and that group is actually really different than the other people. And so when you then just use your sample, you get into trouble. Okay, now what we want to do is we want to see, hey, what happens? Can we actually add cantonal level data to get to better predictors of the cantonal level share. So we're also going to see the cantonal level for the simple model, but we're going to do it when we also have it for a slightly more elaborated model. So here is the official canton by canton outcomes of these like 26 cantons. And then here called RITE-P is, you can go to this URL if you care for the details, but essentially an initiative that was voted on about a year before that is also coming from the same political corner, also one of these classic right populist initiatives that is forced onto the agenda. So we're going to add these two variables. I'm going to smack in the canton ID. I'm going to C-bind it, this new initiative with the canton ID, and I'm going to merge it into an object, which is now called data4. So the only thing I'm doing here is just making sure that for every observation we have in our survey data set, we now see what that person's canton vote share was on that old vote. And we're going to use that as a level 2 explanatory factor. And again, if you're trying to causally explain something, you definitely wouldn't want to be regressing attitudes on attitudes. That doesn't make a lot of sense. But in a measurement step, actually, we're happy to find things that are somewhat close, maybe, even if we don't know the direction or if it's a huge mess in terms of causal errors. So you see now how my model is going to change because I'm now adding here this variable RITE-P. So I'm doing this, and you see when I do so, I have the same issue that I had before. So I still get these like zeros on the realization or the variance of the random effects for women and men, as well as across cantons. The other thing that changes is down here, you see the estimate of the coefficient. So that beta that stands before that X on this slide with the extended model. Now we're going to go through the same setup as before. So I'm taking out the random effects. I'm again creating these pointers. I'm doing.
There's also a question again.
Yeah.
It's it says 538 calculates statistics by weighting surveys by their quality, and they claim that also that their estimates are also accurate. So question is whether you know if anyone has compared their estimates with MRP estimates.
So those are different things, no? Because what they care for is coming up with some form of estimate. And if they go on the subnational level, then it is because they have so many subnational surveys. But what this is doing is a methodology that allows you to use a single survey to dig down to the subnational level. And that's not the same, no, as using a bunch of different surveys, because that approach, of course, works when you care for presidential elections, because there's going to be so many surveys. But usually in our applied work, we have very specific concepts, attitudinal constructs that we try to tap into and come up with measures. And in those cases, we usually don't have a huge set of surveys that we could then think about weighting individual surveys. Also, if I'm not mistaken, then the weights that 538 is using is based on past performance, meaning you're only going to be able to assign weights if you have actually over time often observed a specific poll or company and then compare that to the actual vote outcomes. Again, that's something that is not going to be so easy when you care about whatever, public opinion towards women wearing the veil in school and things like that. Okay, so up until here, nothing has changed. But now we're going to have to take a quick look at these two lines. So before we were just adding in the fixed effects part of the model, but we can't do this now because if we look at this, now we get the intercept, but we also get this beta for right parties. So what we're going to do is we're only going to add in the constant, and we're going to store this like beta coefficient of this level 2 variable and call it beta 1. And now when I go into this step that again looks like the one before, you're going to see that there's a slight difference here. Yeah. So before we just had this element and then the random effect for cantons. And now we need to remember that we have this context level variable which changes over cantons. So we're always going to then add beta 1 times the correct value. So times the vote share for this older right populist vote. Now I'm going to translate it again back to predict the probabilities because this was all happening on the latent. And then this step actually we don't need to do because we do have the object A, it still exists from before. So let's take a look at our overall national estimate. Okay, something didn't work out. Did I not run this line? No, I did. Let me just run through everything again. There we go. Okay, so now we get an estimate of 58.11%. Now you might say, wait, before we had 51.01, this is getting a little worse. So A, if we do the full setup and we illustrate uncertainty and everything, these two things are essentially the same. Note also that we're currently just focusing on the national mean, and that is not necessarily what we, especially the academic interest in this is. We're now going to go in a next step and actually look at the individual cantonal predictions, and that's where we're going to see why this matters. So to come up with cantonal estimates, I'm now going to have to take these 48 ideal types per canton. I'm going to have to multiply them with their relative frequency. So multiply them with the number of people of that specific ideal type and then divide by how many people are in such a canton. And so the structure here is again similar, but what you're going to see is I'm now only reading out one slice of that census object because I know it has 26 columns and each column stands for one of the cantons. And then I'm going to do here the cantonal specific estimate, and I'm going to save that into the object called MRP minaret 2. Then I'm going to do the disaggregation result. So we're just going to take these like 680 people or so. We're just going to look how many people in a specific canton said yes, and that's our estimate. We already know this is not going to look good. And I'm also, for our first MRP model that didn't have any level 2 explanatory factor, I'm going to generate the cantonal estimates. Okay, and now what we want to do is we want to look at how do these estimates fare when we plot model-based estimates against actual outcomes on a cantonal level for the various models we had here. And that plot looks something like this. So you have here the 45-degree line. So if we had perfect data, perfect model, perfect world, essentially all our estimates should be on this line, meaning we would have perfect estimates. The light blue, diamonds that you see, those are the disaggregation results. And you see how that is just like noisy and off the charts, yeah? And then what you get is MRP without level 2 explanatory factors. That's just the empty blue circle. And you see this empty blue circles are here. And then you get the slightly larger filled blue circle. And that is the cantonal estimates based on an MRP model with level 2 information. So that's where we added this right populist initiative that was from a year before. And what you see when you look at this a little bit is like the model without the level 2. If you were to draw a line, a fit, you would see that it's kind of too steep, yeah? Meaning for the ones where we get kind of a low estimate, we are overestimating. And for the ones where we get a relatively high estimate, we're underestimating. And that is not by chance. This is something that you can see. This is most often happening when you're working with small samples. What that is part of this shrinkage towards zero. We're not really good at fully getting into the full spread. But by adding an explanatory variable that is likely correlated with what we're trying to measure, you see how what happens is that if you were to draw a line through these like filled blue points, it becomes much closer to the 45-degree line. Not perfectly, but it's not as steep anymore as it was for the hollow dots. Going to wait quickly in case there's questions up till here.
I think there are two questions. So there's one by Tristan on the whether the Model 1 MRP estimates are very different from the weighted survey estimates. Maybe that means the estimates from the multi-level regression without post-stratification to the one with post-stratification. I'm not sure if that's the right interpretation.
My hunch is it refers to what would have happened if we would have just used post-stratification.
Okay, yeah.
Yeah, so go ahead and try that. The differences are probably not very large here because we see that the one thing that would help us usually getting also differences across cantons into that cantonal random effect doesn't apply in this illustration because it was estimated as zero. And the other thing is that we know that it's mostly due to education. And so if you, of course, fix for education, you're already going to get fairly close to the true estimate. But again, on average, you will outperform a pure post-stratification setup. And no later than at this point, when we're trying to get these cantonal level estimates, you will see that with pure post-stratification, you're not going to get as good results as if you use level 2 explanatory factors. There was a second question.
Yeah, the second question is on the random effect. So what are the consequences for the model results if the canton random effect and the gender random effect random effects are zero?
Yeah, well, that's actually something we can look at. Let me see. So these are from our first model, 48. So specifically because that was generated in the loop up here, that was for the last canton. So for the canton of Jura, these are estimated supports by the 48 ideal types in that canton. And remember that the first two ideal types, they're the same education and the same age group. They only differ for men and women. And now when you look at the support, you see that this here is identical. And that is because our model, the only way how our model can tell us that two ideal types that only differ due to gender would have a different estimate is if that gender random effect was giving you two different values for women and for men. But if we get a zero for both, that essentially means this is like a model that doesn't see gender. Okay, good. So now in a next step, we're going to take a quick look at how you would go about creating uncertainty. Yeah. So just coming up with a number is not that valuable. We, of course, want to have an understanding and a measure for how precise or non-precise we are. I can't go through the full background of this, but if you've never heard of this approach or seen anything labeled as like pseudo-Bayesian approach to uncertainty, then it might be worth taking a look at Gelman and Hill, their book on hierarchical modeling in the first edition. That's the 2007 one. It's chapter 7 that goes through this logic. What we're going to exploit is that the uncertainty is reflected in the uncertainty of the parameter estimates in the model. And what we can do is we can take such a model and we can say, hey, simulate for every parameter 1,000 realizations, such that the ones that we estimate super precisely, you get 1,000 times almost the same number. And where you have a parameter that comes with a lot of uncertainty, you will see that 1,000 repetitions of that parameter will be fairly different, because that reflects the uncertainty. And we can do that. And then what we realize is that this thing I called block, exactly, it's set up like this. So you see it's this huge beast, which has for all these different slots. So here you see the female random effect realization. Now, because we estimate there's zero variance, it's just going to be 1,000 times zero. But in most applications you will of course see different values. Up here we see the values, what is it, for columns. So it's probably the age groups. Yep. So you see this is the realization for the youngest age group. And in every iteration of this simulation, it changes slightly. On average, it would be exactly what we estimated, but it reflects the uncertainty. So now we have to slightly tweak the code a little bit. You see I'm now writing attributes block $ranif dot female to get out then eventually this object that we care for. So if you look at this, you will see that I don't have now a vector with 2 elements anymore, but I have an array that has on the first dimension 1,000 elements and on the second dimension 2. So you can think of this like a matrix with 1,000 rows with 2 columns. I'm going to do this for all the other random effects. Now, this is getting a little bit more annoying because I have to go from vectors to matrices, but I'm doing what we did before. I'm essentially coming up with a structure where what I have is a matrix that has 48 rows, remember 48 ideal types, and because we're simulating it 1,000 times, has 1,000 columns. And I'm making sure that the right realization for female random effects is at the right position. And I do that for all of these 3 individual level random effects. And then since I now have 3 matrices, I don't like before need to do the row sum cbind command. I can just add these 3 matrices together, which will give me a matrix that has 48 rows for the 48 ideal types, and it has 1,000 columns for the 1,000 simulations. Now we're getting to this part where we're going to add in the information from the level 2. So again, I need to figure out where I am. And then I need to come up with this like level 2 contribution, which is the fixed effects. So the constant plus the share of vote for this right wing issue. And what I'm doing here is I'm using matrix multiplication because that makes my life much easier in terms of code. So I'll quickly show you what this block looks like. I don't have an I, yeah. So if we, there we go. So this would be for the canton of Zurich. We would see you just get a 1 for the constant and you get the vote share they actually had a year before. And if you multiply that now with an object that is 1,000 times 2, is that right? Yeah, 1,000 times 2. Then essentially what we're going to get back afterwards is for every one of these 1,000 simulations, it's going to be the constant plus beta times this x value. And then down here, we just need to remember that we have these 1,000 rows and set this up. And then we can add it on top of these individual contributions. Now I'm going through the same steps as before. I'm going to come up with cantonal estimates, but this time I add this UNC because that refers to uncertainty. And I'm going to do for every one of these 1,000 simulations a cantonal prediction. And because I'm now going to draw a plot, I'm just going to order it according to the vote share for the minaret. That just makes the plot look a little bit nicer. And this is what we get out of it. So what you're seeing here is the estimate. That is what we're plotting up here. And you see that I'm excluding 2 cantons because those are the 2 where we see that the actual true result is not part of the 95 confidence interval. That's about to be expected with 26 estimates. And you see the confidence interval is then just the quantile I get from 2.5 to 97.5%. And so what we see here is not only the estimate, but we also get a sense of how sure or not sure we are about a specific unit. Okay, now we get to Mrs. P, Mr. P's better half. Remember from before, the challenge here would be that in our survey data, we know there's a variable we could exploit on the individual level, but we can usually not use it because we actually don't have the equivalent from the Census Bureau. We don't have that information about the population, so we're going to have to create a synthetic joint. So what we're now going to do is we're going to move to this other issue, Kriegsmaterialverbot, so the ban on exporting army goods. I'm again going to kick out the people that don't have any response on it. We see in the survey, we get 41% of the people saying that they support it, but actually the true outcome was 31.8. So we're like, that's not so great, yeah? We're totally overestimating the support for this initiative. So let's go and see what MRP can do for us. So I'm going to set up a simple MRP model like we've seen before. And now this is one that is nice in the sense, you see, we get actually estimates for the variances, meaning now when we look at the random effects across cantons, there's going to be differences. When we look at the random effects across gender, there's going to be differences. The code now is essentially just copy pasted from above. It's the same steps we need to go through. We need to take out the individual random effects, need to get them in the right order. We need to add them for the individual ideal types, and we need to add the constant. So we do that. Now we're going to come up with predictions for each ideal type, and then we take these because these predictions are still projections on the latent dimension of this binary model, and we translate them into predicted probabilities. Okay. Then we have our census object here. And down here, I'm just going to multiply the predicted support of each ideal type, multiply that with the number of people that belong to that ideal type, and divide by all people. And that will give me an estimate. Okay. So we saw in the survey, we had 41% saying yes, the true result is 31.8, so like 32%. Our MRP estimate just cut our error by slightly more than half because it's at 36%. So it's not perfect, but it's much closer to the true value than the raw survey data. Now, the question is, can I do something more? And one thing you could have said is, well, I actually read up on this issue, and this was one of these super classic left-right questions. Nobody believed this would ever pass, and essentially whoever like self-identifies as left, so that would be at that period mostly if you were voting for Social Democrats or the Green Party, would support it, and everybody who considered themselves non-left would of course vote against it because it infringes on free market economy and whatever. So maybe taking into account that we also know whether these people self-identify as left or not could be helpful. So I'm not even going to take the individual parties. I'm just going to do like a left, non-left. So I'm going to create in the survey data a new variable called left. I'm going to set it 0 for everybody. And then for the people that either support the Social Democrats or the Green Party, I'm going to flip it to a 1. So super simple approach. Then we're going to rerun this model, but we're going to add a random effect on this individual level variable left that identifies you as left voter or not. We're going to take a look at this outcome and notice the size of the variance of this random effect when you compare it to the others. It's no big surprise. Yeah, something is happening there because, of course, most people that self-identify as left would actually have supported this initiative and the others not. So now we're just going to go through the same steps as before. So not that much changes, except note, I'm creating new ideal types. I'm now just going to say there's 96 ideal types. There's the 48 we had before, but now there's 96 because there's the 48 we had before non-left, and then there's the 48 left. So that together gets you up to 96. So I'm taking all the other structures we had before and just saying that I'm going to repeat them twice. And I'm creating a new one called left RE. And here is where I'm just writing in the realization of this random effect for left. And then everything else is as before, adding up. Okay, do that. And now we're going through the creation of these predicted probabilities per ideal type. And now what we need to do is we need to create the synthetic joint. So what I'm going to do is I'm going to do simple Mrs. P. Simple Mrs. P will just assume that if you live in a canton and 30% of the people vote for a left party, then that is also what we're going to do within each ideal type in that canton. We know that's not true, but we actually know that that doesn't add that much noise into the model while it still allows us to gain predictive strength by using that information. So I'm first reading out here per canton, this left variable. So I'm just taking the sample-based strength of left voters as the cantonal strength. So that's a little cheating. Yeah, usually what I would have to do is go look at the last elections, read out that stuff, but I had it already built into my data. So if I now look at this, then you see for the 26 cantons, you end up with varying strengths. Yeah, Canton 6. Rough spot if you're left. Now, that's not entirely true. Part of this is due to what we're using here is electoral returns from the lower house. Well, turns out the lower house in some cantons is a single member district, and we all know that that has different dynamics. So just using party vote share as an indication of the distribution of party preferences in that population is probably off. So we're going to overwrite 6 and 15, those two places where we're most afraid of this, with approximations. So this is definitely where the sausage is made, in the sense of, we could have a long discussion whether this is really the right pick of numbers. And yes, there are more elaborate ways about thinking how to come up with a better estimate of that number. Now what I'm doing is I'm taking for each canton the census object, and if I see that in a specific place the left has 41.8%, then I'm going to take the number of people from a specific ideal type, and I'm going to take 41.8% of that number and assign them to the left version of that ideal type, and I'm going to take 58.2% and assign them to the non-left version. So this is where we're creating the synthetic joint distribution. Now we're going to go through this to generate cantonal level estimates. Up here are the cantonal level estimates without Mrs. P. So that's when you say, hey, I can't get party ID from the census office. My hands are bound, can't do anything. Then we're reading in the actual true electoral outcomes on that issue. We're going to compute the mean squared error. And we're going to look whether Mrs. P is actually Mr. P's better half. And what we find is a reduction from 0.019, that's the mean squared error across the cantons, when you use Mr. P and you say, I can't do anything, I can't add parties. And when you actually say, we do have more information in the survey data that we probably want to use, then you see that you can push down the mean squared error. Okay. I'll wait a second in case any questions come up to Mrs. P. Nothing? Okay. Now, the last thing we're going to look at is auto MRP. So remember here, we might face a situation where we actually would have a lot of context variables that we could use, but we don't know which ones to pick. And we know that it's actually a fairly important decision. One explanation why context level variables might be important is also that your survey data is essentially fixed. You're not going to be adding new variables. Your census stuff is somewhat fixed. So sometimes you can come up with the marginal, like here when we have something like party. But there's a lot of things that are on the level 2 variable available. There's so many data sets, whether this is on states in the US, cantons in Switzerland, Bundesländer in Germany, where you would have a lot of information about these different units that you might want to use. And so auto MRP is one way for you to integrate additional information. Now, the one difficulty here is that we need to first come up with a slightly different structure of our census file. Remember the census object we have, this like 48 times 26. That's where we have all the information. But the way we need to supply that information into the auto MRP function is a little different. So what I'm going to do here is try and translate that into a structure that works for us. So you see how I specify the types. And then here I have this level 2 block where we're putting in urbanization, but we're also putting in education expenses per capita and the left vote share in the parliamentary elections. Okay, and then this is this like overall block we're creating that is going to be called census _ auto _ MRP. And so the code might remind you before, it's again going to be something that has these 1,248 rows. But what it's now going to have is it's going to have 9 columns, and we have to write all the information, like the individual level as well as the context information into it. And that's what's happening here. And I'm also going to have to give these variables the same names that we're then going to use later. And store it as a data frame. Philip, anything important I forgot about the auto MRP census file structure?
No, I don't think so. I mean, you can think of the structure as that each row is one specific ideal type, right, in one specific subnational unit.
Yeah, exactly. So we get that plus then also the information of the level 2, that we have there.
Yeah.
Okay. And yes, this is, this is a little bit the price you pay when you work with MRP, that you actually have this additional data source, the census stuff. That is what is really allowing you to get also better results. But the price you pay is that you suddenly need to do these additional steps that you don't if you're in like this old world where you just have survey data, you look at conditional means, and those are your estimates. And now what you see here is how you use AutoMRP. So AutoMRP is a little bit different. It's not going to ask you for like that you enter your model formula. It's going to ask you for the outcome, and then it's going to ask you for the names of the level 1 variables. Those are the ones where you're going to see random effects then. Then it's going to ask you for the level 2 explanatory variables that you're putting into your model. It's going to ask you for the name of the variable that indicates the different subnational units. Then it's also going to ask you whether you're providing the counts of the ideal types or actually the proportion. And here, the way we set up the data above is proportion. Then you have to say what's actually the data object where the survey responses are in. Then you have to say where's the object where you have all the census information. And then you see how you can turn on or off these individual classifiers. What I'm doing here, just to illustrate now, is I'm only going to run a simple MRP model. So if you want to avoid having to read out your individual random effects and then do all this by hand, you can rely on this package. You just set all these other classifiers to false, MRP to true. And you see, it takes a quick second, tells you that it's skipping EBMA because you only chose one classifier and there's nothing to be model average there. And then you see how we get estimates for each of these cantons. Now, the other thing you, of course, can do is you cannot set them to false. The default is that they're all set as true. And what we're now going to do is we're going to run this model and we're going to see what comes out when we actually use all 5 classifiers. And when we then also use ensemble Bayesian model averaging to come up with our final set of estimates. And let me just quickly check. Yes. So if you run this now at home, this is going to take maybe, I don't know, 10, 15 minutes or so to run. So I actually ran it before we started such that we're not like staring at each other and waiting for the model to perform. And so what I'm going to be doing here now is computing the MSC of the AutoMRP model, that the individual estimates I get out of this element. So if you take a, yeah, that's not right. Yeah. So these are the 26 cantonal estimates that come out. So this is not based on an individual best subset lasso, PCA, gradient boosting, or support vector machine classifier, but based on each of them that are then combined and according to their performance on a holdout data set weighted. And so what I want to do is create this MSE3, because what we can now do is look for this set across these different modeling things you saw. So first we can look at the MSE. If you just like use standard MRP, then what happens if you say maybe using partisan ID of an individual, and then eventually you say, hey, maybe you just add some context level information and let the model sort out how much from each it wants to take. And when we do that, then we see that MRP 0.019, we go down to 0.016, and actually with AutoMRP, we're now down to slightly below 0.01. Okay. Questions?
Maybe you could add that you can speed up the auto MRP model by specifying the number of cores to be used.
Yeah. That's a very good point. Oh, why does it say that? Philip, what am I doing wrong? Can you open a help file in our package?
Sorry, I was muted. Yeah, I can open the help files. If you use the single question mark, for me it comes up.
There we go. Do we have, I need to get this Zoom thing out of the way. Do we have something on the cores in the help file?
Yeah, it should say, like, if you go back, it should say the argument and what it does. Is that what you mean?
Yeah.
Like if you scroll to
X cores.
Yeah, that is.
Did I miss it?
No, you're right there. It's in the middle now. It's like below EBMA size.
Oh, of course. Yes. Sorry. Yeah. So most of you will have more than one core. And so it would definitely make sense to speed that up, to split up, because there's a bunch of things that can run in parallel and don't need to be done sequentially. And that's going to make you much faster. And specifically, once you try to get uncertainty, you will definitely be wanting to do this in parallel. Do we have any more questions in the chat, Philip?
No, nothing new.
Okay. Well, now we're actually even done ahead of time. I was thinking this is going to take longer. So maybe I'll wait a second in case anybody has a question. Okay, if you have any question, this might be the moment to paste something in the chat. Okay, perfect. Well, Olga, are you around?
Yes, I'm here.
Perfect. You don't see any questions from, what was it, YouTube?
Yeah, I've been posting everything that popped up here. There was one question now. Someone couldn't install auto Mr. P package, but I try to handle it, asking what was the error. I don't know. Maybe we'll try to figure this out now.
Okay,
but
perfect.
No more questions other than that.
Okay,
Oh,
well
there's
then
one
that's a wrap.
There's
There's one
also
in the chat, I think.
So Richard Traunmüller and what's his name? Richard Traunmüller and the co-author Claassen. I'm blinking on his first name. They have a paper, if I'm not mistaken, sociological research methods. Because they were interested in attitudinal structures among Muslim immigrants in Western Europe. And so they have worked exactly on how can you use MRP when the small area you care for is not necessarily a geographic group, but more a social group. And it might also pay off for that to take a look at the deep interactions paper in the AJPS by Kitza and Gelman. Okay, well, I hope this was helpful. I hope you find in the next couple of weeks, months, or maybe next year, a good use case and that you can apply this. And I look forward to hopefully seeing many of you post-pandemic at some form of conference or workshop or whatever. Have a lovely time.